to Sleepy Facts with Justin. Tonight, we are going to talk about rain. Find a comfortable position now. Let your body settle. Let your shoulders drop. Let your hands rest softly wherever they feel natural. There is nothing you need to do tonight except listen. Outside somewhere right now, it is raining. In a forest, or over an ocean, or high above a mountain, water is falling gently back to the earth. It has been doing this for a very, very long time. Longer than any of us can truly imagine. Tonight, we are going to follow that water. We are going to learn about clouds and sky and the quiet science behind one of the most soothing sounds the world has ever made. But there is no rush. We will move slowly through everything. And if your eyes grow heavy before we reach the end, that is perfectly all right. That is exactly what this is for. Rain has always had a way of making rest feel possible. There is something deeply ancient about listening to it fall. Long before cities, long before roads and rooftops, our ancestors sheltered during the rain. They paused. They waited. They listened to water moving through leaves and along stone, and in that stillness they rested. Your brain still carries that memory. Scientists have found that the sound of rain lowers activity in the part of the brain that processes fear and stress. It activates something quieter, something more dreamlike, something that says, you are safe. You can slow down now. So let it. Let the idea of rain settle around you like something soft, like a blanket pulled close on a gray afternoon, like the sound of water on glass when there is nowhere you need to be. Over the next several hours, we will move gently through the science of how rain is made. We will visit clouds forming slowly in the sky. We will follow a single raindrop from the moment it takes shape to the moment it touches the ground. We will explore the smell that rises from the earth when the first drops fall. We will travel to rainforests and deserts, to other planets, to ancient oceans that no longer exist. There is so much to discover about something so simple. And yet, you do not need to remember any of it. That is the beautiful thing about tonight. Every fact, every gentle piece of knowledge is here simply to give your mind something soft to rest on, something to drift with, the way a leaf drifts on a current, going nowhere in particular, perfectly at ease with the movement. You might fall asleep somewhere in the first few sections. You might drift in and out. Either way, you are doing exactly the right thing. So take one slow breath in and let it go. The rain is beginning. The water cycle has no beginning. That is the first thing to understand about it, and perhaps the most quietly remarkable thing. It is not a story that started somewhere and will end somewhere else. It is a circle, a slow, continuous turning, water moving from the earth into the sky, and from the sky back to the earth, and back again, and again, without ever truly stopping. The rain that falls tonight has fallen before, not in the same place, not in the same form, but the water itself, the actual molecules of it, have been here for a very long time, longer than the mountains, longer than the oceans as we know them. Scientists have traced the hydrogen atoms in ordinary water all the way back to the beginning of the universe itself, more than 13 billion years ago, when the universe was young and filled only with light and simple elements. Hydrogen was born. That hydrogen is still here. It is in the oceans right now. It is in the clouds forming slowly over the horizon. It is in every raindrop. In you, if we are being honest. The water in your body carries atoms that are older than the sun. Take a slow breath. Let that settle. The oxygen in water is younger, though still ancient beyond imagining. It was forged inside massive stars that lived and died long before our solar system took shape. Those stars burned through their fuel, collapsed, and then exploded outward in enormous bursts of energy and matter. In those explosions, hydrogen and oxygen fused. Water was made and eventually carried on dust and ice and slowly drifting rock. Some of that water found its way to a small planet forming around a young star. Our planet, Earth, was different then. It was hot and violent and newly forming. There were no oceans gentle rains. No quiet forests listening to the sound of water on leaves. There was only rock and fire, and the slow cooling of a world that had been molten almost all the way through, but water was arriving. Steadily, patiently. Some scientists believe it came on asteroids and comets, icy bodies that collided with early Earth and left their water behind. Others believe that water was already locked deep inside the material that formed our planet, and that it slowly worked its way to the surface as the Earth cooled. The truth is probably both. Water came from many directions over a very long time. By about 4 billion years ago, perhaps even earlier, there was liquid water on the surface of the Earth. Think about what that means. 4 billion years ago, the Earth was less than 500 million years old. Life had not yet appeared, or had only just barely begun. There were no continents as we know them. The sky was different. The air was different. The sun was younger and slightly dimmer, and yet water was already cycling, already falling as rain, already evaporating under that pale, ancient sun, already rising as vapor, already condensing again in cool air high above, and falling again to the surface. The water cycle was running before the first living cell drew breath. It has been running ever since, without interruption, for longer than anything alive on Earth can remember. That is what is happening when it rains tonight. Something 4 billion years old is continuing. The water cycle we learn about in school sounds simple when described in a few words. Water evaporates. It rises. It forms clouds. It falls as rain or snow. It flows into rivers and lakes and soaks into the ground. Then it evaporates again, around and around. But inside each of those steps, there is an extraordinary amount of quiet complexity. Let us follow it gently. It begins at the surface. Whenever water is exposed to air in an ocean, a lake, a puddle on a warm pavement, even a single wet leaf, some of that water is always evaporating. Individual water molecules at the surface absorb energy from the sun and gain enough speed to escape the liquid carried by moving air. The ocean is the great engine of this process. More than 70% of all evaporation on Earth happens over the oceans. Every single day, an almost incomprehensible amount of water rises from the sea as invisible vapor and drifts into the atmosphere. The exact amount changes with temperature, with wind, with season, but it never stops. The ocean is always breathing upward. Plants contribute too, in a process called transpiration. Trees and grasses and ferns draw water up through their roots and release it through tiny openings in their leaves. A single large tree can release hundreds of liters of water vapor into the air on a warm day. A forest breathes moisture into the sky. The Amazon rainforest, which we will visit in a later section, produces so much water vapor that it creates its own weather, its own clouds, its own rain. Water rises. As it rises, it cools. And cool air cannot hold as much water vapor as warm air. So the vapor begins to slow and gather and look for something to cling to. Tiny particles in the air, dust, pollen, salt crystals from the sea become the seeds around which water begins to condense. Tiny, almost weightless droplets form around each particle. Billions of them drifting in the air together. A cloud. We will spend more time with clouds in the next section. But for now, just hold the image of them gently. Enormous, slow-moving collections of tiny droplets drifting with the wind. They are made of the same water that was in the ocean, and before that, in a river, and before that, falling as rain, and before that, rising from a forest floor on a summer morning. It is the same water. It has always been the same water. When the droplets in a cloud grow heavy enough, they fall. As rain, mostly. As snow in cold air. As hail in particular kinds of storms. We will come to each of those in time, but tonight we are thinking about rain. Soft and steady and endlessly familiar. It lands on the earth. Some of it soaks into the soil, moving slowly down through layers of rock and sand until it reaches the water table, the vast underground store of water that feeds springs and wells, Some of it flows across the surface, joining streams and rivers that carry it back toward the sea. Some of it is taken up immediately by plant roots, drawn into leaves, and breathed back into the air, and some of it evaporates before it even reaches the ground. In very dry air, a raindrop can fall from a cloud and slowly shrink as it descends, its outer edges turning back to vapor. Scientists call this virga, rain that falls but never arrives. Ghostly curtains of water hanging beneath clouds over the desert, dissolving before they touch the earth. Even this becomes part of the cycle. Ancient peoples understood this intuitively, long before science had the words to explain it. The Greek poet Hesiod, writing almost 2,700 years ago, described vapors being drawn up from rivers by the wind and returning as rain. The ancient Hindus wrote about the movement of water from sea to sky to rain to river and back to sea again. The cycle was observed and felt and named in many cultures, in many languages, long before anyone could trace a water molecule with a microscope or a satellite. They simply watched the rain. They noticed that it always came back. There is something deeply calming in that continuity, in the fact that the water cycle is not fragile, not uncertain, not something that might simply stop one day and leave the world dry. It is ancient. It is patient. It has survived meteor impacts and ice ages and mass extinctions and tectonic upheavals. It ran when there were no animals to watch it. It will run long after any of us can imagine. Tonight, somewhere high above, water vapor is rising from a warm ocean. Somewhere a cloud is forming, slowly and silently. Somewhere rain is beginning to fall. And here, right now, you are resting. You are warm and quiet and still. Let your breathing slow just a little more. There is nothing to do with any of this information except let it drift through you, like rain moving through air, like water moving along the surface of a slow river. The ancient water cycle has been turning for 4 billion years. It will keep turning tonight. You can let go now. You have looked up at clouds your entire life. On slow as a child, lying on your back in a field or a garden, watching shapes drift and dissolve and slowly become other shapes, a rabbit becoming a ship, becoming a long, spreading smear of white against blue. You have watched clouds from car windows on long drives, from the windows of aeroplanes, looking down on the tops of them for the very first time and realizing, with a small and quiet kind of wonder, that they are solid looking from above, bright and white and still, like a second landscape resting below the sky. We have always watched them. Every culture in recorded history has named them, painted them, written about them, used them to predict the weather and the seasons and the moods of gods, and yet the science of how a cloud actually forms, the specific, gentle sequence of events that brings one into being, was not properly understood until quite recently in human history. Tonight, we are going to follow that sequence from the very beginning. A cloud begins with warmth. Somewhere on the surface of the earth, over a sun-warmed stretch of ocean, or a sun-baked field, or the broad leafy canopy of a forest, the air near the ground is heated and warm air rises. It is lighter than the cool air around it, less dense, and so it lifts. Slowly, invisibly, great columns of warm, moist air drift upward from the surface, like breath rising from something sleeping. As this air rises, it moves into a part of the atmosphere where the pressure is lower. And when air pressure drops, air expands. And when air expands, it cools. This is the key. Cool air cannot hold as much invisible water vapor as warm air. The warmer the air, the more vapor it can carry without releasing it. But as our rising parcel of air cools, it reaches a point where it simply cannot carry all of its moisture any longer. The vapor has to go somewhere. It has to change, and so it condenses. But it needs something to condense onto. Pure water vapor, perfectly alone in a perfectly clean sky, can cool a surprisingly long way before it forms droplets on its own. In a completely clean atmosphere, clouds would barely form at all. What makes clouds possible? What makes rain possible? What makes the whole sky work is dust. you sweep from a shelf. Microscopic particles, almost impossibly small. Grains of sea salt lifted by ocean spray, flung high into the air and carried for thousands of miles on the wind. Particles of fine soil lifted from dry ground. Pollen from flowers and grasses, fragments of ash from distant wildfires, sulfur compounds drifting upward from the ocean surface, tiny particles shed by bacteria living high in the atmosphere. Each of these microscopic specks is called a condensation nucleus, a seed, and when rising, cooling air reaches the point where it can no longer hold all of its moisture. That moisture clings to these seeds. One molecule of water, then another, gathering around a particle of sea salt or a fragment of pollen, forming a droplet so small that a single raindrop contains perhaps 1 million of them. These droplets catch the light. Together, billions upon billions of them drifting in the same parcel of cooling air, they become visible. They scatter sunlight. They glow. They form a cloud. The altitude at which this happens, the point at which rising air cools enough for condensation to begin, is called the cloud base. On a clear, warm summer day, you can often see it clearly, a blue sky above. And then, at a precise and almost ruler-flat altitude, the soft white bottoms of cumulus clouds beginning. Every cloud in the sky that day has its base at exactly the same height, because they all formed from air that cooled to the condensation point at the same altitude. The cloud base is a kind of ceiling made of physics, gentle and invisible and exact. Above the cloud base, the cloud can continue to grow. If the air inside the cloud is still warmer than the air around it, it keeps rising. The cloud builds upward. A small, soft cumulus, the rounded, cauliflower-shaped cloud of a pleasant afternoon, might stop at a few 100 meters of height. But in conditions where the atmosphere is unstable and the air very warm, a cumulus can keep climbing. It can become a tower. It can build and build over the course of an afternoon until it has risen many kilometers into the sky, becoming the vast, anvil-headed storm cloud known as cumulonimbus. drop enormous amounts of rain in a very short time. But most clouds are quieter than that. Most clouds are simply drifting slowly, holding their moisture, existing. There are 10 main types of clouds, organized loosely by altitude and by shape. The highest clouds, those drifting at 30,000 feet or more, are made not of water droplets, but of ice crystals. At that altitude, the temperature is far below freezing, and any moisture that condenses does so as tiny, flat, hexagonal plates of ice. Cirrus clouds are these, the thin, wispy, feathered streaks you sometimes see high in a pale blue sky, smeared across it as though brushed with a fine and careless hand. They are beautiful and harmless and impossibly delicate. Each strand is made of ice crystals falling slowly through the upper atmosphere, blown sideways by winds, sometimes moving at 100 miles an hour, stretched into long curving trails. Below them, in the middle layer of the atmosphere, come the alto clouds, altocumulus, rippled layers of small, rounded puffs, often arranged in long rows that make the sky look like the surface of a pale, ribbed beach. Altostratus, a broad gray sheet that softens the sun to a faint, silvery circle, turning the light milky and diffuse, giving the world a quiet, underwater quality. Lower still are the clouds that feel most familiar. The clouds of everyday life. Stratus clouds sit low in the sky, close to the earth. They are gray and uniform, and often featureless. On some days, they descend entirely to the surface, and we call that fog. Walking through fog is precisely walking through a cloud. The droplets are exactly the same. The physics is identical. The only difference is that the cloud happened to form at ground level, where someone could walk into it. And then there is the cumulus, the great round-bottomed, flat-topped, cauliflower-white cloud of summer afternoons. The cloud children draw. The cloud that drifts through paintings and tapestries and poems across every culture on earth. It is formed by thermal convection, warm air rising from a heated surface, cooling as it climbs, condensing at the base, building upward in great rounded towers that glow brilliant white in sunlight. A single cumulus cloud may weigh 500 million kilograms, and yet it floats. It floats because the droplets inside it are so tiny that the air resistance acting on them is greater than gravity's pull. They drift. They never fall, not until they grow. We will talk about that growing, about how droplets become raindrops in the next section. But for now, hold the image of the cloud. 100 million tons of water suspended in the air, made of nothing more than cooling and dust and the invisible physics of pressure, drifting across a blue sky as if it has nowhere to be, and all the time in the world. Clouds have been forming over this planet for 4 billion years. Every civilization that has ever existed has looked up at them. Every sailor has read them. Every farmer has watched them with hope or with worry. Every child has found shapes in them, and every poet who has ever tried to describe something soft and temporary and beautiful has reached, eventually, for a cloud. There is something about them that asks you to slow down. They move on a different time scale than most of what occupies us. A cloud does not hurry. It does not check anything. It simply drifts and changes and eventually dissolves back into invisible vapor, and the sky goes clear, and somewhere else another cloud is already beginning to form. Let your thoughts be like that tonight. Let them drift and change and dissolve without you needing to hold onto any of them. Let the image of a slow white cloud moving across a blue sky be the last clear thing in your mind as you rest deeper into this quiet hour. The clouds are always forming somewhere, and somewhere they are letting go. If you were asked to draw a raindrop right now, you would almost certainly draw a teardrop. A rounded base, narrowing gently to a soft point at the top. It is the shape we have all drawn since childhood. It is the shape on weather app icons and umbrella patterns and the little blue symbols on maps. It is so universally understood as the shape of rain that almost no one ever questions it. And it is almost entirely wrong. A falling raindrop does not look like a tear. It never never has. The actual shape of a raindrop is one of those quiet surprises that science occasionally offers. A small correction to something we all thought we already knew. A gentle reminder that the world is more interesting than our assumptions about it. Let us look closely. It begins in the cloud. A tiny droplet forming around a grain of sea salt or a fragment of dust is so small and so light that surface tension, the force that makes water cling to itself, holds it in a perfect sphere. At this size, smaller than the width of a human hair, the droplet is round in the way that soap bubbles are round. Surface tension pulls equally from all directions, drawing the water into the most compact shape possible. A sphere is nature's answer to the question of how to hold something together with the least possible surface. These droplets drift in the cloud. They collide with other droplets. They merge and grow as long as they are very small, a millimeter in diameter or less. They remain almost perfectly spherical. The forces acting on them are gentle and roughly equal in all directions, but as a droplet grows larger and heavier, gravity begins to win. It starts to fall, and falling changes everything. As the droplet descends, it moves through air, and air pushes back. The resistance of the air presses against the bottom of the falling drop. The leading phase, the part of it that is cutting downward through the atmosphere. This upward pressure from the air flattens the underside of the drop, the bottom, which we might imagine pointing downward like a teardrop's tip, is actually pushed inward and upward. It becomes flat, and then, as the drop grows larger still, slightly concave, curved inward like the bottom of a hamburger bun. The top of the drop, meanwhile, remains rounded. There is less air pressure there. So a medium-sized raindrop, 2 or 3 millimeters across, looks something like a small, slightly squashed sphere, rounded on top, flat, or gently hollowed underneath. Scientists sometimes describe it as looking like an M&M candy, or a jelly bean lying on its side. It is not remotely teardrop shaped. The confusion almost certainly comes from watching water drip from a surface. a leaky tap, a wet leaf after rain, a finger dipped in water and lifted slowly. In these cases, the drop does form a teardrop shape, but only for a fraction of a second, as the last thin thread of water connecting it to the surface stretches and breaks. That brief, graceful elongation is what we remember. That is the shape that lodged itself in human memory and became our universal symbol for a raindrop. But the moment it falls free, it rounds itself out. Gravity and surface tension and air resistance find their balance, and the teardrop becomes a sphere or a bun or something more complex still. Because as raindrops grow larger, they grow stranger. A drop of 4 millimeters begins to look less like a bun and more like a parachute. The air pushing against its flattened underside creates a growing dimple. The center of the drop thins. The outer edges remain thick and heavy. It begins to look from below like the cap of a mushroom or the bell of a jellyfish or an open umbrella seen from above. And this shape is not stable. The larger a raindrop becomes, the more it wobbles and shudders as it falls. The air is not perfectly smooth. It is turbulent, shifting, pressing unevenly. The thin skin of water at the center of a large drop stretches and flickers. Eventually, it tears. The large drop breaks apart into smaller drops, which round themselves back into spheres and fall on independently. This is why raindrops in nature are never very large. The biggest stable raindrops are around 4 to 5 millimeters in diameter. Beyond that, they simply do not hold together. Scientists have managed to create and briefly suspend drops of up to 10 millimeters in laboratory wind tunnels. Enormous, wobbling, umbrella-shaped things. But in the open air, they break apart almost immediately. So rain, by its nature, is self-limiting in drop size. The sky cannot send down marble-sized drops. Physics will not allow it. Every drop that grows too ambitious simply divides, becoming 2 smaller drops, each of which settles gently into a more sustainable shape. Now think about speed. A falling raindrop does not fall forever at the same speed. When it releases from the cloud, gravity accelerates it downward. It gets faster and faster, but as it speeds up, the air resistance pressing against it also increases. Eventually, the two forces, gravity pulling down, air pushing up, exactly balance each other. The drop stops accelerating. It falls at a steady, constant speed. This is called terminal velocity. And for a raindrop, it is surprisingly gentle. A large raindrop, 5 millimeters across, reaches a terminal velocity of around 9 to 10 meters per second, about 20 miles per hour. A smaller drop, 1 millimeter across, falls much more slowly, at perhaps 4 meters per second. The very tiniest droplets, those barely larger than cloud droplets, fall so slowly that a light breeze can carry them sideways faster than they fall downward. They drift, they float, they are almost more fog than rain. This range of speeds is part of why standing in rain feels the way it does. The drops that reach you first at the outer edges of a shower are often smaller and slower. The heavy drops at the center of a downpour arrive with more weight and more speed. The sound they make on leaves, on pavements, on rooftops, is partly the sound of their size and partly the sound of their velocity. A large, fast drop makes a fuller, lower sound. A fine mist of tiny, slow drops whispers. There is one more strange thing about raindrops and speed. Scientists assumed for a long time that all raindrops reached the ground at terminal velocity, that the balancing act between gravity and air resistance was always completed before impact. But in 2009, researchers monitoring 6 major rainstorms and measuring more than 23 million individual drops discovered something unexpected. More than 30% of the very smallest drops, those under 0.5 millimeter, were falling faster than their terminal velocity should allow. The best explanation is that these tiny drops were fragments, pieces broken off from larger, faster drops during the drop's descent. They had not yet had time to slow down. They were still carrying the speed of their larger parent drop, like small pieces of something that had been moving fast and could not immediately forget it. even in falling rain, there are mysteries that were only noticed in 2009. The world does not run out of things to quietly surprise you. So the next time rain falls against a window beside you, or on a roof above you, or across an open field somewhere in the soft middle distance, you can hold a slightly different image in your mind, not teardrops falling, not the neat little symbols from the weather forecast. Instead, imagine tiny spheres, millions of them, some perfectly round and small, drifting down so gently they could almost be carried sideways by a breath, some larger, slightly flattened, wobbling as they fall, pressing through the air with their broad faces leading. Some at the very edge of stability, their centers thinning, their edges heavy, shuddering with the effort of holding themselves together, and some that could not hold, broken apart mid-fall into smaller, rounder drops that reset and continue downward. Each one a small, temporary piece of physics, each one made of the same ancient water that has been cycling through this sky for 4 billion years. Each one falling gently toward the earth. Let your breathing slow now. Let the image of those drops become something soft and formless, not something to study or remember, just a gentle sensation. Water moving through air in shapes nobody draws correctly, falling quietly, arriving softly, asking nothing of you in return except that you listen. The rain is still falling somewhere. You can still hear it if you let yourself. A cloud droplet is extraordinarily small. If you could hold a single one between your fingers, which of course you cannot, it would evaporate before you got close. It would be perhaps 20 micrometers across, 20 millionths of a meter. A human hair is roughly 3 times as wide. It is so light, so nearly weightless, that the gentle updrafts of air inside a cloud hold it suspended almost indefinitely. It does not fall. It drifts. It circles slowly in the dark interior of the cloud, carried up on warm currents, settling a little when the air stills, rising again. And yet this same droplet, given the right conditions and enough time, becomes a raindrop. A raindrop is about 100 times wider than a cloud. If you are thinking about that in terms of volume, it is not 100 times larger. It is roughly 1,000,000 times larger. One raindrop contains approximately 1,000,000 cloud droplets. The distance between a cloud droplet and a raindrop, that millionfold journey, is what this section is about. There are two main paths a droplet can take to become rain. Two different mechanisms working in different kinds of clouds in different parts of the world under different conditions, and both of them are extraordinary. The first is the simpler of the two to imagine. It is called collision and coalescence, and it is exactly what it sounds like. Inside a cloud, droplets are not all the same size. Some are larger, some smaller, and size determines how fast they fall. A larger droplet falls faster. Its terminal velocity is greater than that of a smaller one. So, as the larger droplet drifts downward through the cloud, it overtakes the smaller droplets in its path. It collides with them. Some of those collisions result in the two droplets bouncing apart. But most of the time, particularly when the droplets carry slightly different electrical charges, which is common inside clouds, they merge, they coalesce. The larger droplet grows, and as it grows, it falls faster still. And falling faster, it collides with more droplets, and each collision makes it larger, and each increase in size makes it faster. It is a gentle cascade, a slow accumulation, like a snowball rolling down a very gradual hill, gathering mass so quietly that nothing dramatic seems to be happening, until suddenly you realize the thing has become quite large. This process, collision and coalescence, is the main way rain forms in warm clouds, particularly in tropical regions. Warm, deep clouds over tropical oceans, filled with relatively large droplets and strong updrafts that keep the droplets in play for a long time, can produce rain through this process alone, without any ice ever being involved. The clouds that bring afternoon downpours to a rainforest or a tropical coast are often warm cloud systems, producing rain through nothing more than droplets finding each other in the dark and choosing to stay. but in the middle latitudes, where most of the world's population lives, including everywhere with 4 seasons and cool winter rains, warm cloud coalescence alone is often not enough. The clouds are cooler. The droplets are smaller. A different mechanism takes over. And it was discovered in a genuinely beautiful way by a meteorologist walking through a mountain fog. His name was Tor Bergeron. It was the 1920s, and he was living in Norway, often walking in the forested hills near his home. He noticed something that anyone else might have dismissed entirely on cold days when fog lay thick among the trees. The fog droplets clung to the branches, coating them in a fine glaze of ice and moisture. But below a certain temperature, below about -10 degrees Celsius, something changed. The fog near the ground was different. There were fewer droplets in the air. The fog was thinner, and the branches were coated not in tiny clinging droplets, but in something more solid, in ice, in frost. Bergeron understood what he was seeing at those very cold temperatures. Some of the fog droplets were freezing. They were becoming ice crystals, and the ice crystals, once formed, were doing something remarkable. They were stealing moisture from the liquid droplets around them. The reason comes down to a subtle difference in physics. In freezing air, water vapor much prefers to attach itself to ice than to liquid water. The vapor pressure near an ice crystal is slightly lower than the vapor pressure near a liquid droplet, so water vapor migrates, drifting away from liquid droplets and depositing itself, molecule by molecule, onto the ice crystal surfaces. The ice crystals grow. The liquid droplets shrink. The fog thins. This is the Bergeron process. And it is the dominant way that rain forms over most of the temperate world for most of the year. High in a cold cloud, in the layer where temperatures drop below freezing, a small number of cloud droplets freeze. They become ice crystals, thin and hexagonal, formed around dust particles or certain kinds of biological material that are particularly good at initiating freezing. Around these crystals, the moisture in the air begins to deposit. The crystals grow larger and larger, while the liquid droplets around them surrender their water and shrink. As the ice crystals grow heavy enough, they begin to fall. And as they fall through layers of the cloud, they collide with more liquid droplets, which freeze onto them, building up layers of ice in a process called accretion. The growing crystals sometimes stick to one another, forming snowflakes, loose, branching structures of ice that fall more slowly and gently than solid ice pellets. Then something remarkable happens for those of us watching from below. These ice crystals and snowflakes, born in temperatures far below freezing, fall out of the cloud base and into warmer air beneath, and they melt gently and gradually as they descend through layers of above freezing air. The ice becomes water again. The snowflakes dissolve into rounded drops. The ice pellets soften to liquid. What began as a frozen crystal high in a cold cloud arrives at the ground as rain. Most of the rain that falls outside a tropical window, most of the rain that soaks into a European field or a North American forest, started its life as ice. This is one of those facts that takes a moment to settle. A warm summer rain, the kind that arrives on a July afternoon and feels almost body temperature when it touches your arms, soft and slightly warm, and utterly unlike anything frozen. And yet, just a few kilometers above your head, that rain was ice. It was snowflakes falling through the cold, dark interior of a cloud, melting in the warm, lower atmosphere with about 10 minutes to spare before reaching your skin. The sky performs this trick billions of times each day, all over the world. Cold rain becoming warm rain, ice becoming water, a process of freezing and melting, and arriving that nobody notices because the ending, the warm touch of rain on a summer afternoon, gives no hint of how the journey began. And then there is the downpour, a sudden heavy rain, the kind that arrives in minutes and drenches everything, is simply the collision and burgeoning processes operating at full intensity inside a particularly deep and vigorous cloud, a cumulonimbus tower, climbing many kilometers into the sky has a vast interior in which both processes can run simultaneously. Ice crystals growing in the frozen upper reaches, warm cloud coalescence happening lower down, strong updrafts keeping droplets in the cloud longer, giving them more time to grow enormous before they finally escape downward. And then the cloud releases all of it at once. Billions of large, heavy drops, the accumulated wealth of a deep and ambitious cloud. And the world below goes from dry to drenched in what feels like moments. A downpour is the sky doing everything at the same time, as quickly as it can. And a gentle, barely there drizzle is the same processes running quietly in a thin and shallow cloud, producing only the smallest drops, which float more than they fall. Between those two, the downpour and the drizzle, lies the full, soft spectrum of rain. Wherever you are tonight, whatever rain sounds you carry in your memory, the heavy summer storm, the thin gray drizzle of a November afternoon, the tropical downpour that turns streets into rivers within minutes, all of it came from the same place, tiny droplets drifting in the dark interior of a cloud, finding each other, growing slowly, or crystals of ice building themselves in frozen silence before melting into something soft. All of it eventually finding its way down, all of it eventually arriving quietly. You do not need to do anything with any of this. Let it simply drift through your thoughts like a cloud, moving through its own slow interior. Let your breath settle a little lower. Let the weight of the day become just a little more distant. The drops are still forming somewhere above you, patient and quiet and unhurried. There is a smell that almost everyone knows. You may have noticed it before the rain even arrives. Standing outside on a warm, dry afternoon, with a dark sky building on the horizon, and the air beginning to move in that particular, expectant way. And then it reaches you, something earthy and cool and deeply familiar. Something that feels less like a smell and more like a memory, like the inside of a greenhouse on a cloudy morning, like soil after the garden has been watered, like the world exhaling something it has been holding quietly for a long time. That smell has a name. It is called Petrichor, and the story of how it was discovered and what it actually is and why we can smell it at all is one of the loveliest quiet stories in science. The word itself is relatively new. It was coined in 1964 by two Australian researchers, Isabel Joy Baer and Richard Thomas, working at the Commonwealth Scientific and Industrial Research Organization in Canberra. They had been investigating a phenomenon that everyone could smell, but no one had formally explained. The particular pleasant, earthy odor that rises from soil when rain falls on dry ground. For their scientific paper, they needed a name for it. They reached into ancient Greek, Petra meaning stone or rock, and ichor in Greek mythology, the ethereal fluid that flows through the veins of the gods. Not blood, something finer, something that cannot be seen in the ordinary way, but is nonetheless real and powerful and present. Petrichor, the ichor of stone, the blood of the gods, released from the earth when rain arrives. It is one of the most beautiful compound words in any scientific vocabulary. But what is it exactly? Petrichor is not a single thing. It is a blend, a chord of different compounds released by different sources, combining in the open air into something that the human nose perceives as a unified, distinctive scent, and unpacking each of its ingredients reveals an entire hidden world living just beneath the surface of every patch of soil. The most important ingredient, the one that carries the most weight in the final scent, is called geosmin. Geosmin is produced by bacteria, specifically by a family of soil-dwelling bacteria called actinomycetes, and within that family, most abundantly by a genus called streptomyces. These are ancient organisms, filamentous, branching, colonial bacteria that weave themselves through soil like a slow and patient network. They are found almost everywhere on Earth where there is soil, in gardens and fields and forests, and the banks of rivers, and the margins of deserts. They are extraordinarily common. During dry periods, streptomyces and its its relatives produce spores. They are waiting out the drought, holding themselves in a kind of biological stillness, conserving energy, patient as the soil itself. And while they wait, they produce geosmin. They release it into the spaces between soil particles, where it clings and accumulates during the dry weeks or months. Then the rain arrives. A raindrop striking dry soil does something remarkable. It does not simply soak in. It hits with enough force to trap a tiny pocket of air beneath it. That air bubble collapses and bursts upward through the surface of the drop, releasing a spray of microscopic droplets, an aerosol, a fine mist that carries into the air whatever was dissolved in the surface water, including geosmin. The trapped, earthy scent of weeks of dry soil, aerosolized in a fraction of a second by the impact of a single raindrop drifting away on the air. Multiply that by millions of raindrops across a field, billions across a hillside, and the smell arrives before the rain does. Because aerosol particles are light and travel on the wind ahead of a storm. Long before the first drops reach you, the petrichor they will release from soil further upwind is already drifting toward you, carried on the same moving air that brought the clouds. The smell of rain approaching is, literally, the smell of rain that has already fallen somewhere nearby, drifting to you on the wind like a small announcement of what is coming. Now, the human nose's sensitivity to geosmin is extraordinary. We can detect it at concentrations as low as 5 parts per trillion. To put that in some kind of perspective, 5 parts per trillion is like a single drop of geosmin dissolved into 200 Olympic-sized swimming pools. We can smell it at that dilution. We are among the most sensitive detectors of geosmin of any animal on Earth. Far more sensitive than we are to most other chemical compounds. Why would human beings have evolved such a refined sensitivity to something produced by soil bacteria? The most plausible answer is water. For most of human evolutionary history, finding water was one of the most important tasks our ancestors faced. Rain meant water. The smell of rain the geosmin released when rain struck dry earth was a reliable signal that water was near or had recently fallen nearby. A person sensitive enough to smell that signal from a great distance had an advantage. They could orient toward it, follow it, survive a dry season that others could not. Our exquisite sensitivity to Petrichor may be, in other words, an ancient survival tool, a gift from our deep past, the same instinct that makes the smell of rain feel so immediately, wordlessly good, so much like relief, may be the echo of a time when it genuinely meant survival. There is also a separate but related smell that often accompanies rain, particularly during or after a thunderstorm. A sharper, cleaner, electric smell, slightly metallic, slightly sharp, unmistakable. That is ozone. Lightning splits oxygen molecules in the air. Some of those freed oxygen atoms rebind not in pairs, as ordinary oxygen is, but in threes. This three-atom form of oxygen is ozone. It is the same molecule that forms a protective layer high in the atmosphere, absorbing ultraviolet radiation. Near the ground, it is produced briefly and locally by lightning. The wind carries it ahead of the storm, and we smell it, crisp and electric, and utterly unlike the earthiness of geosmin, more like the air around a photocopier than the soil of a forest. It is nevertheless woven into our sense memory of stormy weather. And then there is a third ingredient, less discussed, but always present in the full complexity of Petrichor. Plants, during dry periods, produce oils. These are compounds that accumulate in the soil and on rock surfaces, particularly on clay-rich soils and certain sedimentary rocks. During dry spells, yellowish, waxy oils that cling to mineral surfaces and build up quietly over weeks of dry weather. When rain arrives, these oils are released into the air alongside the geosmin and the microbial aerosols. They add a slightly green, slightly resinous note to the overall scent. Sharper in some environments, in desert soils, after the first monsoon rain. These plant oils contribute enormously to what many people describe as the most powerful and moving petrichor smell they have ever encountered. The first rain on desert soil is a singular sensory experience. The word Madi Ka Adder means, roughly, the scent of the earth. In the Uttar Pradesh region of India, artisans were distilling this scent, capturing petrichor in oil form. As far back as the records go, they would press dry clay into sandalwood oil and steam distill the result, extracting a perfume that smelled unmistakably of rain on dry earth. By the time Bear and Thomas, formally named Petrichor, in 1964, this ancient perfume tradition was already thousands of years old. People have always known this smell, long before science explained it, long before the word existed. It was bottled and traded and worn on skin and given as gifts, this distilled essence of rain beginning. There is a quiet wholeness to that. The most advanced atmospheric chemistry, the most sophisticated gas chromatography, eventually arrived at the same conclusion as an artisan in ancient India who simply knew that something beautiful happened when rain touched dry earth and wanted to carry it with them always. Tonight, whatever you remember of rain, the smell of it arriving in the heat of summer, the cool green scent of a garden after an afternoon shower, the sharp electric charge of the air before a thunderstorm. That is petrichor. That is geosmin drifting from soil and ozone from lightning and ancient plant oils released from clay and stone. That is bacteria that have been waiting patiently in the dark, finally releasing the molecules they made during a long dry spell. That is the world recognizing rain, and you recognizing it too, down in some deep place below thought, below memory, where the smell of rain still means, very quietly, that everything is going to be all right. Let that feeling settle now. Let it move through you slowly, the way a smell moves through an open window. Something soft, something ancient, something that has been arriving for a very long time. Not all rain is the same. We use one word for it, as if it were a single thing. Rain. But rain comes in many shapes and temperaments. It arrives softens the air around you, or as heavy drops that bounce visibly off the pavement. It can fall warm or cold, or in a form that freezes the instant it touches whatever it lands on. It can fall from a towering black cloud in the middle of a sunny afternoon, or drape itself over an entire landscape for 3 gray days without ever quite becoming a proper downpour. There is a whole family of rain, and each member of that family comes into being through a different set of circumstances, a different reason for air to rise, to cool, and to let go of its moisture. Tonight, we will visit each of them in turn. The first is convective rain. And if you have ever lived somewhere warm and humid, anywhere near a tropical coast, or in the American South, or across the Caribbean, you know it well without ever needing to have named it. Convective rain is afternoon rain, sun rain, the kind that arrives on a clear morning that gives very little warning, a blue sky, a warm and humid day, and then, as the sun reaches its peak and the earth heats, and the air above begins to rise and rise and rise, enormous towers of cloud build upward with visible speed, cumulus becoming cumulonimbus, a white tower becoming a dark tower, and then, often quite suddenly, a downpour, heavy and warm, and sometimes accompanied by lightning, as intense as it is brief. The whole event, from the first drops to the last, might last 40 minutes. Then it moves on, or simply collapses as the updraft cools and the sky begins to clear and the world steams gently in the returning sun. The second type is orographic rain, or, as it is sometimes called, relief rain. And it is the rain of mountains. When a parcel of moist air traveling across the ocean encounters land, particularly land that rises steeply, it has nowhere to go but up. The air cannot push through a mountain range. It must climb over it. And as it climbs, it cools. And as it cools, it reaches the point at which it can no longer hold all of its moisture. Clouds form. Rain falls, sometimes persistent, soaking rain, falling on the windward side of the mountain, while the summit catches cloud after cloud. What happens on the other side of the mountain is equally interesting. The air, having dropped much of its moisture on the windward slopes, descends, and descending air warms, and warming air can hold more moisture again. So the leeward side, the downwind side, is often strikingly dry. This is called the rain shadow effect. Two valleys, separated by a single range of mountains, can have entirely different climates. One green and wet and richly forested, the other brown and dry and sparse. In the permanent lee of the same peaks that send rain to its neighbor. The western coasts of continents, the Pacific Northwest of North America, the western shores of Norway, the west coast of New Zealand's South Island, are among the wettest places on Earth, partly because they catch orographic rainfall from every moist ocean airstream that moves inland. Some of those places receive several meters of rainfall every year, nearly all of it forced upward and released by the mountains immediately inland. The third type is frontal rain, and it is the rain most familiar to people in temperate climates, in northwestern Europe, in the northeast of North America, in much of southern Australia. It is the rain of gray skies and long days, and the particular English relationship with weather. Frontal rain forms where two air masses meet. A warm, moist air mass traveling from a tropical ocean, and a cold air mass pressing down from the polar regions. These two bodies of air do not mix easily. They have different temperatures, different densities, different amounts of moisture. At the boundary between them, the front, the warm air is forced to rise over the denser, heavier cold air. It cools as it rises. Its moisture condenses. Clouds spread across the sky, not in a single dramatic tower, but in a wide, layered sheet that can extend for hundreds of kilometers. And then it rains. Frontal rain is not usually dramatic. It does not arrive in bursts and vanish. It comes steadily, evenly, sometimes for many hours or many days, as a slow-moving front passes through. It is the rain that makes a day feel like a different color. Gray-green and quiet and interior, the kind of rain that makes you glad you are inside. makes the glow of a lamp seem warmer and a blanket seem softer, and the outside world seem thoughtfully removed from wherever you are right now, between and around these three main types. Rain also comes in subtler forms. Drizzle is its own particular thing. Not truly rain by the technical definition. Drizzle drops are smaller than 0.5 millimeter in diameter, tinier than proper raindrops, but more than just fog. Drizzle hangs in the air. It seems to arrive from all directions at once, dampening you so evenly and completely that you cannot quite identify when it began. It forms in shallow, stratiform clouds, low, flat, gray clouds that sit close to the earth and produce precipitation through the gentlest collision and coalescence, without any great drama of ice or storm. A drizzly day has a particular quality to it, a softness, a muted, slightly melancholy softness that many people in private find rather soothing. Then there is freezing rain, which looks like rain, falls like rain, but is not, in its consequences, anything like ordinary rain. Freezing rain begins its fall as ice crystals or snowflakes high in a cold cloud. Then it falls through a layer of warmer air and melts, becoming liquid water. Then it falls further into a very thin layer of cold air near the ground, too thin, too brief for the drops to refreeze in the air, and arrives at the surface, still liquid, but the surface is below freezing. And the instant the drops touch anything, a road, a branch, a power line, a blade of grass, they freeze. Not in loose crystals, but in a perfectly clear, perfectly smooth sheet of ice. The world after freezing rain has a strange, terrible beauty to it. Every branch coated in transparent ice, catching and bending the light. Every surface a mirror. Every step a negotiation. The weight of accumulated ice on trees can bring down branches that have stood for decades. Power lines snap. Roads become impassable. And over it all, this eerie, glittering silence, the world transformed into something that looks like glass. There are also warm rains and cold rains, light rains and heavy rains, each with its own numerical definition tradition in meteorology. A light rain falls at less than about 2.5 millimeters per hour. A moderate rain at between 2.5 and 7.5 millimeters per hour. A heavy rain above that. During the most intense tropical downpours, rain can fall at more than 50 millimeters per hour. Nearly 2 inches of water accumulated in 60 minutes, and there is virga, rain that falls but never arrives. The ghostly curtain of precipitation hanging beneath a cloud in dry desert air, each drop slowly evaporating before it reaches the ground. A melancholy sight. Rain that tried all of these, from the violent tropical convective storm to the barely there drizzle drifting sideways on a coastal morning, are rain. The same water, shaped by different atmospheres and different temperatures and different conversations between warm air and cold, between ocean and mountain, between the tropics and the poles. Each one has a different sound. The heavy tropical downpour drums. The frontal rain hisses steadily. The drizzle barely whispers. Freezing rain ticks and chimes on glass. Each one says something slightly different to the part of you that has been listening to rain your entire life. Wherever you are tonight, there is likely a type of rain that feels most like home to you. The one that arrived most often outside the windows of the places you grew up. The one that matches some quiet interior landscape you carry without thinking about it. The one that, when it starts, makes some part of you exhale. Let that rain fall quietly in your mind now. Whichever one it is, let it fall steadily, the way it always has. You do not need to stay awake for any of it. We live at the bottom of an ocean. That sentence was written in 1644 by an Italian scientist named Evangelista Torricelli, and it is one of the most quietly beautiful observations in the history of science. Not an ocean of water, but an ocean of air. A vast, invisible sea of atmosphere pressing down on us from every direction, held in place by gravity, miles deep, weighing on the surface of the earth with a force of about 1 kilogram, pressing on every square centimeter of everything it touches. We do not feel it. We have never felt it. We were born into it and grew up inside it, and our bodies are perfectly calibrated to exist within it. But it is there always, the weight of all that air above us, pressing down with a steady, enormous patience. And the changes in that pressure, the invisible, slow breathing of this ocean of air, are what make the weather. Torricelli came to his ocean of air by a strange and brilliant route in 1643. He took a glass tube about a meter long, sealed at one end, and filled it entirely with liquid mercury. He then placed his thumb over the open end, inverted the tube, and lowered the open end into a bowl of mercury. When he removed his thumb, the mercury in the tube fell, but only partway. It settled at a height of about 76 centimeters above the surface of the mercury in the bowl, leaving a perfect vacuum in the sealed space above it. Nothing held the mercury up. No suction, no magic. The weight of the atmosphere pressing down on the mercury in the bowl was exactly balanced by the weight of the mercury column in the tube. The air pushed on the bowl, and the mercury pushed back up inside the tube. And where those two forces balanced, the mercury rested. Torricelli had invented the barometer, a device for measuring the weight of the air above it, and almost immediately he noticed something important. The height of the mercury changed from day to day. Some days it was a little higher, some days a little lower. The air was not always the same weight. Its pressure changed. This was the key that eventually unlocked weather forecasting. Air pressure changes because air moves, and air moves because of temperature. Warm air is less dense than cool air. Its molecules are moving faster and taking up more space, so warm air tends to rise. And when air rises away from the surface, it leaves behind a region of lower pressure, a space where there is less air sitting on the ground than there is nearby. This region of lower pressure draws in air from the sides, trying to equalize. Air flows inward from surrounding higher pressure areas. And as that inrushing air arrives and meets in the center of the low pressure region, it has nowhere to go but up. It rises and cools, rising, cooling air is exactly the recipe for clouds, for rain. A low-pressure system is, at its heart, a pump that draws in moist air from its surroundings, forces it upward, and produces clouds and rain almost as a byproduct of its own existence. Weather forecasters learned this over centuries of careful observation. When the barometer fell, when the mercury dropped, rain was coming. Sailors read their barometers the way they read the sky, looking for the same message written in different languages. A falling barometer meant rising air somewhere nearby. Rising air meant clouds. Clouds meant rain. And at sea, rain often meant the leading edge of something much more serious. The opposite is equally instructive. A high-pressure system forms where air is sinking. Cool air descending from above compresses as it sinks, warming adiabatically. That is, warming simply due to the increase in pressure, without any heat source needed. Sinking, warming air is the enemy of cloud formation. Warm air can hold more moisture as vapor. When it descends and warms, whatever clouds existed in it evaporate away. The sky clears. The sun comes out. The barometer rises. A high-pressure system brings beautiful days. Clear blue skies, calm winds, settled weather. Farmers loved a rising barometer. Sailors relaxed. The world felt orderly and benign. But it is worth pausing to appreciate the elegant symmetry here. High pressure brings clear skies, not because it pushes clouds away, but because it prevents them from forming at all. Sinking air simply dissolves clouds before they can build. The sky is empty of cloud not because something removed the clouds, but because the conditions that create them, rising, cooling air, are absent. The two systems move across the surface of the earth in great spiraling patterns, shaped by the rotation of the planet. In the northern hemisphere, air spirals clockwise around a high-pressure center and counterclockwise around a low. In the southern hemisphere, the directions are reversed. This spiraling is caused by the Coriolis effect, the deflection of moving objects by the rotation of the earth beneath them. The result, seen from space, is one of the most striking features of our planet. The swirling cloud patterns visible in satellite images from weather services around the world, those great white spirals and curves and bands of cloud, are the signature of pressure systems rotating across the face of the earth. They are not random. They follow precise physical rules. The spiral of a low-pressure system over the North Atlantic, bringing rain to Ireland and gray skies to London, is shaped by the same force that shapes the spiral of a tropical cyclone over the warm Pacific. Scale and intensity differ enormously, but the physics is the same. And between the great pressure systems, the air flows. Wind is simply air moving from high pressure to low, from where there is more of it to where there is less. The steeper the pressure gradient between two systems, the greater the difference in pressure between them, compressed into a short distance, the faster the wind blows. A gentle breeze is a gentle gradient. A gale is a steep one. It is useful to imagine all of this not as abstract physics, but as something more like breathing. The atmosphere breathes. It fills and empties. Pressure rises in one place and falls in another. Air flows between them, carrying moisture and temperature from one part of the world to another. A warm, wet air mass from the Gulf of Mexico, breathing northward into the central United States. A cold, dry air mass pressing southward from the Arctic. When they meet, the warm air rises over the cold, the pressure drops, and it rains. The barometer on someone's wall or their weather app is measuring one small piece of this vast, continuous breathing. When it falls somewhere above, air is rising. Somewhere above, clouds are forming. Somewhere above, 1,000,000 tiny droplets are beginning to find each other in the dark. The rain is coming. There is something deeply restful about understanding why the sky does what it does. It removes a kind of ambient uncertainty, the vague feeling that weather simply arrives, unpredictable and capricious, for its own reasons. The rain is not arbitrary. It is not random. It is the entirely logical and beautiful consequence of air having weight and temperature affecting density. and rising things cooling, and cooling, releasing moisture. Rain is the atmosphere making sense. And sitting with that, with the idea that the gray sky outside follows rules as reliable and ancient as gravity, has a particular kind of reassurance to it. The ocean of air above you is doing exactly what it has always done, breathing in and out, rising where it is warm, sinking where it is cool, forming clouds in the places where it rises, clearing them in the places where it sinks. It has been doing this for 4 billion years. It does not need you to monitor it. Let the pressure drop a little in your own body now. Let the weight of the day be like a barometer settling gently downward, Mercury finding its level, everything equalizing into something quieter and more still. The atmosphere is breathing above you. You can simply breathe along with it. Inside a thunderstorm, the air is at war with itself. Vast columns of warm, wet air are climbing at extraordinary speed. Updrafts, sometimes moving at over 100 miles per hour, carrying raindrops and ice crystals and hailstones upward, as if the sky were trying to swallow the storm from below. At the same time, heavy cold air is rushing downward beside these updrafts. Warm rising, cold falling. The two currents existing side by side, separated by invisible boundaries, churning the interior of the cloud into something turbulent and powerful and alive. And somewhere in all of that churning, in the violent collisions between ice crystals and hailstones and supercooled water droplets, something electric is happening. Charge is separating. The exact mechanism is still not fully understood, even now. But the dominant picture is this. Inside a deep storm cloud, ice crystals and hail collide constantly in the fierce updrafts. When they collide, electrons are transferred. Smaller, lighter ice crystals tend to acquire a positive charge. Larger, heavier hailstones tend to acquire a negative charge. The updraft carries the lighter positive crystals upward toward the top of the cloud. The heavier negatively charged hailstones fall or are suspended lower down. Over time, the top of the cloud becomes becomes positively charged. The middle and lower portions become negatively charged. The charge separation grows, and the negative charge, accumulating at the base of the cloud, repels negative charges on the ground directly below it, leaving the ground beneath the storm positively charged. Between the base of the cloud and the ground, an electric field builds. It grows stronger and stronger as the separation of charge increases. And then the insulation of the air between cloud and ground fails. Air is normally a very good insulator. It resists electrical flow. But when the voltage across a gap becomes large enough, air ionizes. Its molecules shed electrons and become electrically conductive. If only for an instant, a channel of ionized air begins to reach downward from the cloud. Scientists call this the stepped leader. It is invisible to the naked eye, descending in discrete jumps, each step a few tens of meters long, branching as it goes, following the path of least resistance through the air. Simultaneously, from the highest points on the ground below, tall trees, buildings, hilltops, upward streamers of positive charge reach, upward toward the descending leader. They cannot be seen either. They are rising and seeking when a stepped leader and an upward streamer meet. When the descending channel of negative charge connects with the rising channel of positive, the circuit is complete. And in a fraction of a second, a massive discharge of electricity travels back up the channel, not downward, upward. The brilliant white flash of lightning visible from miles away is mostly a return stroke traveling from ground to cloud, moving at roughly 1/3 the speed of light. The whole event takes about half a second. The channel through which it travels is approximately as wide as a human thumb. The temperature inside it, in that half a second, reaches about 30,000 degrees Celsius, 5 times hotter than the surface of the sun. And it is that extraordinary heat that makes the thunder. The air along the entire length of the lightning channel is superheated almost instantaneously. It expands in an explosive shockwave. The expansion is so fast and so powerful that it creates a pressure wave, a sound wave radiates outward from every point along the channel simultaneously. Close to the strike, this arrives as a single, sharp crack further away, because different parts of the channel are at different distances from you. The sound from different points arrives at slightly different times, spreading out into the long, low, rolling rumble that moves across the sky for several seconds. Thunder rolls because lightning is long. A single bolt may travel 3 or 4 kilometers through the air. The sound from the far end of that bolt reaches you a second or two after the sound from the near end. The rumble is the thunder from one flash, arriving in sequence, and the gap between the flash and the first sound tells you how far away the storm is. Light travels at 300,000 kilometers per second, fast enough that the flash reaches your eyes almost instantly. Regardless of distance, sound travels at about 340 meters per second. So, for every 3 seconds between flash and thunder, the lightning was roughly 1 kilometer away. For every 5 seconds, roughly 1 mile, a gap of 15 seconds means the storm is 3 miles distant and moving, perhaps, toward you or away from you. A gap of 5 seconds means it is close. A gap of nothing at all, flash and boom, simultaneous, means it is directly overhead, and it is time to be somewhere else. Most lightning never touches the ground. About 3/4 of all lightning discharges happen entirely within the cloud, between regions of opposite charge inside the same storm. These intra-cloud bolts illuminate the whole cloud from within, turning it briefly into a vast, glowing lantern. On a night when a distant thunderstorm is too far away to hear, when you can see only the silent light flickering along the horizon, you are watching intra-cloud lightning, sometimes called sheet lightning. The storm becomes, from a distance, a slow and silent light show. Enormous energy expending itself in silence. On Earth, at any given moment, there are approximately 2,000 thunderstorms in progress somewhere around the world. Together, they produce roughly 100 lightning strikes every second. Every second, 100 times, somewhere on this planet, the air is briefly 30,000 degrees, and a thumb width of sky is briefly as bright as the sun. And yet here, where you are, it is quiet. That distance, the distance between the storm and the stillness, is one of the most comforting things about being safely inside when lightning is somewhere nearby. The world contains storms of extraordinary violence, and you are not in them. The rain is falling somewhere out there, and the lightning is illuminating clouds that you cannot see, and the thunder is rolling across landscapes that are far from wherever your body is resting right now. There is a particular quality to the sound of a distant thunderstorm. When you are safely inside, with the rain against the windows and the thunder arriving muffled and low, and rolling from somewhere several miles away, there is nothing alarming about it. There is something almost ancient in how calming it is. How the body, knowing it is sheltered, reads the sound of a storm the same way it might read the sound of a river, as background, as texture, as proof that the world outside is alive and vast and doing what it has always done. Lightning has been striking this planet for as long as it has had a substantial atmosphere. Scientists believe that in early Earth's history, when the atmosphere was thick with volcanic gases and storms, were continuous and global, lightning may have struck billions of times more often than it does today. Some researchers believe that the energy of early lightning was one of the conditions that enabled the first complex organic molecules to form. That lightning and rain together may have contributed to the chemical soup from which life eventually emerged. The storm that flickers somewhere outside tonight is perhaps a very faint echo of those first storms. The same physics, the same charge separation, the same explosion of heated air, the same long, low, rolling sound, billions of years older than anything that could listen to it, and still arriving, still illuminating, still rolling across the dark. Let it roll. Let the sound of a distant storm, remembered or imagined, be something loose and far away from wherever your thoughts are resting, something that belongs to the outside world, moving through it on its own terms, requiring nothing from you. The lightning finds its path without your help. The thunder rolls out to where it needs to go. And here, wherever here is, the air is quiet, the air is cool, and you are still. There are places on this earth where it rains almost every single day. Not the gentle frontal drizzle of a gray, temperate afternoon. Not the brief convective burst of a summer storm that arrives and passes within the hour, but real, persistent, daily rain. Rain that comes in the afternoon with a kind of reliability that makes it feel less like weather and more like a ritual. Rain that falls so consistently, so generously, year after year after year, that the land beneath it has had millions of years to respond, to adapt, to build something extraordinary out of all that water. These places are the tropical rainforests. They cover only about 6% of the Earth's surface. But within that 6% lives more than half of all the animal, insect, and plant species on Earth. More than half of all the complexity and variety and strangeness and beauty that land-based life has produced in 4 billion years of trying, compressed into a sliver of the map, held together by water and warmth and the daily discipline of rain. To understand why, you have to understand what rain does to a forest over an unimaginably long period of time. In a temperate forest, the seasons impose a pause. Winter comes. Things stop. The trees pull their energy inward. Animals slow or migrate or hibernate. The cold and the dark interrupt the process of life, resetting it annually, keeping complexity in check. The pace of evolution and competition slows to the rhythm of the year, but in a tropical rainforest, there is no winter. There is no frost. There is no season of genuine cold, no period of significant drought, no annual interruption. Rain falls most days. Temperatures are warm and steady. The sun is strong. The growing season is not a season. It is every day, every month, every year, indefinitely. And so the competition for resources, for light, for water, for space, for the attention of pollinators and seed dispersers, never stops. it intensifies instead over millions of years into a complexity so dense and so intricate that scientists have spent careers in a single hectare and still not cataloged everything living there. The architecture that emerges from this competition is the layered structure of the rainforest itself. At the very top, rising above everything else, are the emergent trees. These are the giants, trees that have won the long competition for light by simply growing taller than everything around them, lifting their crowns above the general canopy to bask in full, unfiltered sunlight. They may reach 60 or 70 meters in height. Their trunks are sometimes buttressed at the base by great flanged roots that spread across the forest floor like the fins of a rocket, stabilizing a mass of wood and leaf that rises as high as a 20-story building above them. These emergent giants are exposed. They feel the full force of wind. They experience the full heat of the tropical sun. They stand above the forest like sentinels, isolated, dramatic, their branches hosting a particular community of creatures suited to exposure: harpy eagles, scarlet macaws, the highest living canopy lizards, insects found nowhere else. Beneath the emergent layer lies the canopy proper. This is the roof of the forest, a dense, interlocking mat of leaves and branches at 30 to 45 meters above the ground, where the canopy trees press their crowns together so tightly that from above the forest looks continuous, like a vast green carpet with barely a gap in it. The canopy is where most of the rainforest's life is concentrated. An estimated 70 to 90% of all rainforest species live in the canopy layer, not on the ground, not in the understory, but up here in the warm, light-drenched green world of the upper branches. Spider monkeys swing between crowns. Tree frogs sit motionless on leaves, their green-on-green camouflage making them nearly invisible. Orchids grow not in soil, but directly on tree branches, their roots exposed to the air, absorbing moisture from the humid atmosphere directly. Epiphytes, plants that grow on other plants, parasitizing them. Cover every available surface, creating miniature ecosystems of their own within the larger ecosystem. Some bromeliad plants hold pools of water in the cup formed by their leaves. Small, private ponds suspended 20 meters above the ground, complete with their own microorganisms, insect larvae, and frog tadpoles. Then there is what happens to rain when it meets this canopy from above. A heavy tropical downpour arriving at the top of the rainforest canopy does not simply pass through it. The canopy intercepts it, transforms it, disciplines it. The broad leaves absorb the initial force of the drops. They direct the water along leaf surfaces and down stems in small, organized rivulets. They drip from leaf tips. Leaves in the rainforest have evolved a distinctive drip tip, a pointed extension at the end that channels water away from the leaf surface quickly, preventing the growth of algae and fungi that might otherwise colonize a perpetually wet surface. By the time the rain that fell onto the top of the canopy reaches the forest floor several stories below, it has been completely changed. What arrived as a driving downpour has been broken up, slowed, and redistributed. It arrives at ground level as a fine, gentle drip. A soft, continuous mist filtered through layer after layer of leaf and branch. The forest floor is dim and still and perpetually damp. Only about 1% of the sunlight that reaches the top of the canopy makes it all the way down to the ground. Walking on the floor of a tropical rainforest during rain is a strangely sheltered experience. The storm that is hammering the canopy 60 meters above is reduced by the time it reaches you to a whisper. The forest absorbs the rain's energy. It takes the violence out of it. It delivers the water gently, on its own terms, in its own time. The Amazon rainforest does something even more extraordinary with all this rain. It makes more of it. The trees of the Amazon collectively release so much water vapor through transpiration, exhaling moisture from their leaves in the same way that we breathe water vapor when we breathe out, that they generate their own clouds. The moisture rises from the canopy, condenses, and falls again as rain. This cycle has been called a flying river, an invisible river of water vapor moving through the atmosphere above the Amazon basin, carrying as much water as the Amazon River carries in its physical channel, delivering rainfall to places thousands of kilometers away from where that moisture first evaporated from a leaf. The rainforest does not simply receive rain. It participates in rain. It is both consumer and producer. It drinks and then breathes back out. And what it breathes out becomes clouds. And what the clouds release becomes rain. And the rain returns to the forest and is drunk again and breathed out again. The loop is closed. The water is local. The forest and the rain are not separate systems. They are one system, cycling the same water through the same trees season after season, generation after generation, for tens of millions of years. There is something deeply restful about imagining the inside of a rainforest at night. The canopy far above, dripping quietly. The air close and warm and smelling of something green and faintly sweet, alive with the sounds of tree frogs and insects, and the soft movement of water along invisible paths down the trunks of giant trees. The darkness under the canopy is soft darkness, not the hard dark of a room with the blinds drawn, but a green-tinted, humid dark, full of the small sounds of living things going about their patient business, and over all of it, the rain. Not loud down here, muffled, transformed, arrived at last after its journey through 60 meters of leaf and branch and epiphyte and bromeliad and moss. Patient rain, quiet rain, rain that has been filtered through more living things than you could count in a lifetime of trying. Let that image settle into you now. The dark canopy above, the soft, filtered drip reaching the forest floor, the warmth and the green smell, and the long, patient hush of a forest that has been receiving rain for 50 million years and knows exactly what to do with it. You can let go of everything except this. The rainforest is still breathing, and so are you. Most rain never touches land at all. Of all the rain that falls on this planet every day, the drops forming in all the clouds above all the continents and all the ocean basins and all the wide, featureless stretches of open sea. Roughly 90% of it falls directly back into the ocean. 90% falling from clouds that formed over water, returning to water, completing their small local cycle without ever coming near a rooftop or a leaf or a person waiting at a bus stop. Rain is predominantly a conversation between the ocean and the sky, an enormous, continuous, mostly private exchange happening out there over vast stretches of water that no one ever sees, in every hour of every day, in every season. Only a small fraction of rain is the rain we know. The rain with an audience. The ocean covers about 70% of the surface of the earth. It is the engine of the water cycle in the most fundamental sense. More water evaporates from the ocean's surface every year than from all the land surfaces of the world combined. The ocean exhales. It lifts water into the atmosphere constantly, endlessly, and that water eventually comes back as rain, mostly falling somewhere. Most of it, as we have just learned, falling right back where it came from. But what happens when rain meets ocean is not simply water returning to water. Something more interesting happens when rain falls onto the surface of the ocean. It arrives as fresh water. Rain is chemically almost pure water. The salt that evaporated from the ocean was left behind when the water molecules rose as vapor. What goes up is fresh. What comes down is fresh. And fresh water is slightly less dense than salt water. It does not immediately mix in. Instead, a rainstorm over the ocean creates something scientists call a freshwater lens, a thin, buoyant layer of less salty water resting on top of the heavier, saltier ocean below, spreading outward from where the rain fell, persisting for minutes or hours, or even days, depending on how calm the sea is and how heavy the rain was. These lenses are invisible from above. They leave no mark on the surface that you could see from a ship or a plane, but instruments can detect them. The water is slightly cooler where the cold rain fell. is measurably less salty in the very calm, warm waters of the tropical ocean, beneath heavy convective rainstorms. Freshwater lenses can stretch for kilometers across the surface, floating like a thin film of difference above the ocean that produced the water in the first place. The boundary between the lens and the saltier water below is called a halocline, a sharp gradient of salinity packed into just a few centimeters of depth. Within that thin boundary, the ocean is briefly, locally, in a state of stratification that affects how heat moves, how nutrients circulate, how marine life behaves near the surface. A rainstorm over the ocean leaves a record written in salinity and temperature, slowly erased by waves and current and time, until the lens mixes in and the surface returns to its ordinary composition. The ocean remembers rain in other ways too. Scientists have discovered that the saltiness of the ocean's surface is one of the most reliable maps of rainfall on Earth. Where it rains heavily and often in the tropics, near the equator, along the tracks of storm systems, the ocean's surface is measurably less salty. The constant input of fresh water dilutes it. Where evaporation dominates over rainfall, in the subtropics, in the great oceanic deserts far from storm tracks, the surface is saltier. The water concentrated by the loss of fresh water to the atmosphere without enough rain to replace it. Reading the ocean's salinity is reading the history of rain. NASA and the European Space Agency have launched satellites specifically designed to measure ocean surface salinity from space, building global maps of where the rain has been. The saltiness of the sea, seen from orbit, becomes a record of all the rain that fell or didn't fall in the months and years before. The ocean and the rain are in constant correspondence. The ocean writes letters in evaporation. The sky replies in rain. And the ocean keeps the record. There is one place on Earth where this correspondence is most intense. A band around the equator, a few degrees of latitude wide, where the trade winds of the northern and southern hemispheres converge, where the warmest ocean water on Earth sits beneath the most consistently rising air, where clouds build daily into the tallest, most rain-productive structures in the atmosphere. It is called the Intertropical Convergence Zone. Sailors have known it for centuries by a different name, the doldrums. A region of light and shifting winds, of frequent heavy squalls, of days where the sky turns black at noon and empties itself, and then, hours later, recovers to something calm. The doldrums were feared by sailing ships, not because they were dangerous in the way storms are dangerous, but because their light and erratic winds could leave a vessel motionless for days or weeks, drifting with no steerage in the swell. What the sailors were experiencing was the atmospheric consequence of the ocean being very warm and the air above it being very unstable. The convergence of two great hemispheric wind systems, pouring their energy and moisture upward into daily convective storms, rain on the equatorial ocean, falling back into the equatorial ocean. The great loop of water at its most concentrated. From space, the intertropical convergence zone appears as a bright, wide band of cloud girdling the earth, a permanent feature of the planet's appearance from orbit. It shifts slightly north and south with the seasons, following the zone of maximum solar heating. But it is always there, always raining, always building and releasing and building again. Beneath it, in the deep blue equatorial ocean, the surface is cooled slightly by all that rain, freshened by all that fresh water, marked by the passage of the storms overhead. The ocean receives it all patiently. It mixes and adjusts. It carries the fresh water southward and northward in its great circulation systems, distributing the memory of the rain across the global ocean over the months and years that follow. And then there is the quieter side of the relationship, not the great tropical storms and the equatorial rain bands, but the ordinary, unremarkable exchange that happens on a gray afternoon over the North Atlantic, or a drizzling evening over the Southern Ocean, far from any shipping lane. Rain falls on an empty sea. There is no one to hear it, no shore nearby to collect it, no forest to transform it, no city to drain it away. It simply falls onto moving water, and the drops add their small percussion to the surface, and the fresh water lenses form and dissolve, and the ocean records it briefly in its salinity and temperature, and then forgets it, absorbed into the deep average of millions of square kilometers of water. And yet something happens even here. The drops, as they fall into the ocean, make sound. As we explored in an earlier section, each raindrop trapping a tiny air bubble, each bubble vibrating at its own frequency, producing a note over the open ocean during a heavy rainstorm. This sound travels downward through the water, spreading out into the deep. Marine biologists studying the soundscape of the ocean have found that rain at the surface is one of the loudest natural sounds detectable far beneath the waves. A broadband hiss that travels for hundreds of meters downward, briefly filling the ocean with sound the way thunder fills the sky. Whales and dolphins, navigating and communicating in the upper ocean, experience a heavy rainstorm as a temporary disruption of their acoustic world. A flood of broadband sound that masks their calls and their echolocation. They dive deeper or move away, waiting for the rain to stop and the ocean's ordinary soundscape to reassert itself. Even far beneath the surface, the rain leaves a trace. The ocean knows when it is raining. There is something in all of this that feels like relationship. The ocean and the sky exchanging water across the ages. The ocean giving up its moisture, the sky giving it back as rain, the rain writing its brief, dissolving records in salinity and temperature. The currents carrying those records across basins and hemispheres, distributing the history of rainfall to the deep Atlantic, the Indian Ocean, the quiet, cold reaches of the Southern Sea, all of it moving, all of it connected, all of it cycling through itself in the same patient loop it has been following since water first gathered on this planet. Tonight, somewhere out over the open ocean, rain is falling on water that no one will ever see. It is falling quietly, without an audience, making its small bubbles its brief freshwater lenses, its faint cooling of the surface, and the ocean is receiving it, as it always has, as it always will. Imagine waiting for rain for 8 months. Not the brief, tense wait of an afternoon when clouds have been building since noon and the air has turned heavy and the first drops feel like relief. Something longer and deeper than that. 8 months of dry air. 8 months of a sky that delivers light, but no water. 8 months of watching the land grow pale and cracked and quiet, while the wells lower and the rivers thin, and everything that grows draws its resources inward and waits. And then, on a particular morning in June, announced sometimes by the arrival of a specific bird, or the smell of something different in the wind, the air changes. A different wind begins, warm and heavy, and coming from the south, crossing thousands of miles of ocean, carrying all the moisture of a warm sea inside it. Clouds begin to build in the afternoon. The temperature drops. The sky turns the color of a bruise, and then it rains. Not a shower, not a storm that passes in an hour. The rain arrives and stays. It rains that day, and the next day, and the day after that, for weeks and months. The rivers swell. The fields fill. The wells recover. Everything that has been waiting begins to grow. This is the monsoon. The word comes from the Arabic mosun, meaning season. It was Arabic and Indian ocean traders who gave the wind its name. Sailors who had noticed, long before anyone understood the atmospheric science, that the winds over the Indian Ocean reversed direction twice a year with extraordinary reliability. For half the year, the winds blew from the northeast, dry and steady, pushing ships from India toward Africa. For the other half, they reversed and blew from the southwest, warm and moist, pushing ships the other way and bringing rain to the subcontinent. The monsoon was both a weather system and a trade wind, a seasonal clock that sailors, farmers, and merchants had been reading for at least 2,000 years before a meteorologist first tried to explain why it happened. The explanation, when it came, was elegant and simple in its essentials. Land heats up faster than water. In spring and early summer, the vast landmass of Asia absorbs heat from the strengthening sun and warms rapidly. The air above it heats and rises. A great region of low pressure develops over the Indian subcontinent and extends into Central Asia. Meanwhile, the Indian Ocean, slower to warm, more thermally stable, remains comparatively cool, with higher pressure sitting over it. Pressure seeks to equalize. Air flows from high to low. The cool, moist air over the ocean begins moving northward and inland, drawn toward the hot, low-pressure continental interior. As it moves over land, it rises over the heated ground. It cools. Its moisture condenses. It rains, and it keeps raining for as long as the pressure gradient maintains itself, for as long as the land is hotter than the sea. In South Asia, this lasts roughly from June to September. 4 months of rain, arriving after 8 months of dry. The Indian subcontinent receives about 70% of its entire annual rainfall during these 4 months. The numbers become almost difficult to hold. Cherrapunji, in the northeastern Indian state of Meghalaya, is one of the wettest places on Earth. In an average year, it receives about 11 meters of rainfall, 36 feet of water from the sky. In the record year of 1861, it received nearly 23 meters. In a single month, July of that year, it received 9 meters of rain. 9 meters in a month, 30 centimeters of rain falling on average every single day. And yet, even Cherrapunji experiences an almost completely dry winter. When the monsoon retreats and the winds reverse. The monsoon is not simply a weather event. In India and across South and Southeast Asia, it is the organizing principle of life. Everything, agriculture, architecture, festivals, literature, music, clothing, even the structure of time is organized around the monsoon's arrival and departure. Farmers across the subcontinent have, for millennia, planted their major crops in anticipation of monsoon rainfall. The Kharif crops, rice, sown as the rains begin and harvested as they end. A good monsoon means a good harvest. A failed monsoon means something much darker. Historical records show that the great famines of Indian history correspond closely with years of severely reduced monsoon rainfall. Years when the shift of the ITCZ was late or weak or incomplete, and the rains that came were not enough. The rise and fall of civilizations has followed the rhythm of the monsoon. Researchers studying cave formations in northern India have traced changes in monsoon intensity across thousands of years and found those changes aligned with the growth and decline of the Indus Valley civilization, one of the ancient world's most sophisticated urban cultures. A centuries-long weakening of the monsoon, beginning around 4,500 years ago, appears to have contributed to the abandonment of major Indus Valley cities. The rain changed. The civilization changed with it. And yet the cultural response to the monsoon has not been one of fear or helplessness. Quite the opposite. In India, the arrival of the monsoon is among the most joyful events of the year. Cities and villages celebrate. Children run into the first rain. Artists painted. Musicians have written ragas, the ancient melodic frameworks of classical Indian music, specifically composed to be played during the monsoon. Their patterns and intervals designed to evoke the particular emotional quality of rain. After a long, dry heat, these monsoon ragas are played in the evenings as the clouds build, or late at night when the rain is steady, and their slow ascending phrases are said to carry in them the feeling of relief, of something long awaited finally arriving. The monsoon is not merely endured, it is welcomed, celebrated, loved. The Indian monsoon is the largest and most dramatic of the world's monsoon systems, but it is not the only one. Monsoon-type rainfall patterns exist across much of tropical Africa, in Southeast Asia and northern Australia, in parts of South America, and even in the American Southwest, where the North American monsoon brings summer thunderstorms to Arizona and New Mexico after months of spring dryness. Each of these systems follows the same fundamental pattern: the seasonal reversal of wind, the shift of the ITCZ, the exchange between hot land and cooler ocean, the release of months of pent-up moisture in a few weeks or months of rain. The planet breathes this way, not in the short breath of a passing storm or the moderate breath of a frontal system moving through in a day or two, but in deep seasonal breaths. Half a year of dry, half a year of wet, following the sun as it moves north and south of the equator across the months, pulling the wet band of the ITCZ with it, delivering rain to one hemisphere and then the other. There is something almost meditative about that scale. To encounter the monsoon in its full form, to sit in a small room in a city in India or Bangladesh or Vietnam, as the rains arrive and fill the street outside with the sound of water on every surface, every car and roof and leaf and stone contributing its own small note to the overall percussion, is to encounter rain as something entirely larger than weather, as something closer to a force of nature in the deepest sense, something that has shaped this land and this culture and these crops and these songs and these stories for thousands of years, and to know that it will come back next year and the year after and the year after that, following its ancient circuit, drawn by heat, pushed by pressure, falling on fields that have been waiting for it since October. The waiting is part of it. The arrival is part of it, and somewhere right now, in the long approach to another monsoon season, someone on the other side of the earth is watching the sky and smelling something different in the wind, waiting with a very particular kind of patience for rain. Let that patience settle into you now. The long, patient waiting of a dry land, the certainty that the rain will come, the deep biological trust that the season will turn and the sky will open and the fields will fill. You do not need to wait for anything tonight. It is already here. Fog is a cloud that has come down to earth. That is not a metaphor. It is the literal, physical truth. Fog and cloud are made of exactly the same thing. The same microscopic water droplets formed by the same process of cooling air, releasing its moisture around the same condensation nuclei of dust and salt and pollen. The only difference between a cloud and fog is where it sits. A cloud sits in the sky. Fog sits on the ground. Walk into fog and you are, without question, inside a cloud. There is something remarkable about that, something that collapses the distance between the unreachable sky and the world we move through. Children understand this instinctively. Adults tend to forget it until someone points it out again. And then, for a moment, the fog becomes something different, not an inconvenience or a hazard, but a visitation, the sky descending, the atmosphere arriving at eye level to be touched. Fog forms by several different pathways, each with its own character and its own particular quality of light and movement and mood. The most common is radiation fog, and it is, in a sense, the fog of stillness. It forms on clear, calm nights, particularly in autumn and early winter, when the absence of cloud cover allows the ground to radiate its heat away into space unimpeded. The ground cools quickly. The air closest to the ground cools with it, chilled by contact. And if that air carries enough moisture, it cools past its dew point. The temperature at which it can no longer hold all of its water as invisible vapor, and the vapor condenses into droplets. Fog forms just above the surface, sometimes only a meter or two thick, sometimes building over the course of a long, cold night into a dense layer many meters deep. Radiation fog loves valleys. Cold air is denser than warm air, and on still nights it drains downhill, pooling in low-lying areas the way water pools in the lowest point of a bowl. Valleys collect the cold. Valleys collect the fog. A hillside on a foggy autumn morning may be entirely clear. The slopes in thin sunlight, the air above crisp and blue, while the valley below is filled to its brim with a white, motionless sea of fog that covers every house, every road, every tree, leaving only the highest rooftops and church spires poking through the surface into the clear day above. Seen from above, valley fog is one of the most beautiful sights in meteorology. A white lake, perfectly still, filling the contours of the land as if poured from above, with every hill and ridge emerging from it like islands in a pale sea. Advection fog is different. It does not wait for night and stillness. It moves. It forms when warm, moist air travels over a cold surface, most often a cold ocean current or a cold stretch of ground, and is cooled from below until its moisture condenses. The fog that rolls in from the sea on a summer afternoon along certain coastlines, the famous fogs of San Francisco Bay, the har that drifts in off the North Sea onto the Scottish and Yorkshire coasts, the sea fog that can descend on a coastal summer morning with startling speed. These are all advection fog, warm oceanic air encountering cold upwelled water near the shore, condensing, drifting inland on the sea breeze, filling harbors and streets with a damp, slightly salty murk that smells unmistakably of the sea. The har, that word alone, is worth lingering with. A Scots and Northern English dialect, word for the cold sea fog that arrives from the east, off the North Sea, usually in spring and early summer, when the sea is still cold from winter, but the land has begun to warm. It arrives silently, often erasing the town behind you as you walk. A gray wall of moisture moving at the pace of a gentle wind, muffling sound, softening edges, reducing the world to what is immediately close. There is a quality to fog that no other weather phenomenon quite replicates. Rain changes the world acoustically and texturally. Snow changes it visually and thermally. But fog changes it spatially. It compresses the world. It removes distance. It takes the broad, horizontal openness of the visible landscape and replaces it with a small, intimate bubble, perhaps 20 meters, perhaps 50, perhaps 100, beyond which everything dissolves into white. The world in fog is smaller, but more intensely itself within that smallness. The tree that is 10 meters from you is rendered with absolute clarity. Every branch and leaf sharp and wet and close. The things that are 20 meters away are suggestions. The things that are 50 meters away do not exist. Writers and painters and photographers have always been drawn to fog for exactly this reason. Dickens opened Bleak House, the longest and arguably the greatest of his novels, with a fog passage that extends for nearly 2 pages, describing fog everywhere, on the river, in the marshes, on the heights, in the rigging of ships, drooping on the gunwales of barges, creeping through the keyholes of street doors. Fog as the atmosphere of a novel about the obscuring of truth by law and power and self-interest. Fog as the outward expression of what the legal system does to clarity. The Japanese artistic concept of Ma, the beauty of negative space, of what is not there, finds one of its purest expressions in fog. A mountain half hidden in cloud is, in Japanese aesthetic tradition, more beautiful than the same mountain fully revealed. The partial view invites the imagination. The hidden half belongs to the viewer's mind as much as to the mountain's reality. Fog as an invitation to imagine what is beyond it. And then there is mist, which is simply thinner fog. The distinction is practical rather than scientific. When visibility drops below 1 kilometer, meteorologists call it fog. Above 1 kilometer, it is mist. Mist is the gauze curtain to fog's heavy drape. A misty morning has a gentleness to it that even a light fog lacks. The world is softened but not erased. Hills in the middle distance are blurred at their edges. The low sun, if it appears, is diffused into a pale disk that illuminates without dazzling. Everything looks slightly watercolored. There is also the fog that forms inside a valley after rain, evaporation fog, or sometimes called steam fog. When cold air moves over warm, wet ground, immediately after rain has soaked a warm field, for instance, or across the surface of a warm lake in cold air. The moisture evaporates from the warm surface and almost immediately condenses back into the cold air just above. It rises in thin, wispy columns, like the steam from a warm bath, drifting upward and dissolving. The ground seems to breathe. A field after summer rain, with thin wisps of evaporation fog rising from the warm grass into cold early morning air, is one of the more quietly magical sights that ordinary countryside can offer. No mountains required, no dramatic scenery, just a field and some recent rain, and the temperature doing what temperature does at dawn, and the result being something that looks like the earth is dreaming. There is a German word, Sehnsucht, that is usually translated as a deep, bittersweet longing for something not quite nameable, a yearning for a place or a time or a feeling that you cannot quite locate or return to. Misty mornings and foggy valleys produce something close to this in many people. A feeling of quiet beauty that carries with it, somehow, a note of sadness. Not unhappy sadness, more like the particular sadness of a beautiful piece of music that ends. Perhaps it is because fog is temporary. It always lifts. It always will. The sun rises, or the wind picks up, or the temperature shifts, and the droplets evaporate back into invisible vapor, and the world returns to its ordinary clarity. The tree that was mysterious and close becomes just a tree again. The valley that was a white sea of fog becomes just a valley. You never quite get to hold onto fog. It knows you are watching it, and it leaves, but for the time it is here, drifting gently, compressing the world to what is near and soft and immediate, muffling the distant and the demanding, filling the air with a fine, cold moisture that settles on every surface like a memory of rain. For that time, the world is quieter and gentler and more interior than it usually is. The fog asks nothing of you. It simply arrives and softens everything and stays for as long as it stays. Let the fog come in around your thoughts now. Let the edges of things soften. Let the distant and the complicated dissolve into a gentle white that requires no attention. Only what is nearest and softest remains. There are places on this earth where it almost never rains. Not dry places in the way that a summer month without rain feels dry. Not the mild seasonal drought of a Mediterranean summer, or the brown dustiness of late August on a temperate hillside, when the the grass has gone pale and the ground has hardened. But everyone knows the autumn rains are coming, something much more absolute than that. There are places where years pass without a single drop, where decades pass, where, in the deepest and most ancient cores of certain deserts, no meaningful rain has fallen within the span of recorded human memory. The Atacama Desert in northern Chile is the driest place on Earth. It lies in a narrow strip along South America's Pacific coast, squeezed between the Andes Mountains to the east and the cold Humboldt Current Ocean water to the west. Both of these geography act as walls against moisture. The Andes block the wet air of the Amazon basin. The cold ocean water beneath the coastal air prevents evaporation and discourages the formation of rain clouds. The result is a double lock, a place from which moisture is excluded from both directions at once. In the core of the Atacama, average annual rainfall is less than 1 millimeter. Some weather stations there have operated for decades without recording a single rainfall event. Some areas of the desert are believed to have received no significant rain in 500 years. 500 years of dry sky, 500 years of morning and evening and stars, and cloud shadows that promised nothing and delivered nothing. 500 years of dust, and yet life is there. Patiently, stubbornly, ingeniously there. Some of it lives in the soil. Microscopic organisms called extremophiles that have adapted over millennia to a world almost entirely without water, extracting the last traces of moisture from morning fog that drifts in from the coast, from the tiny amount of water locked in mineral salts in the soil. These microbial communities are among the most isolated and ancient on Earth. Scientists study them partly because the Atacama is the closest analog on Earth to the surface of Mars. Cold, dry, mineral-rich, bombarded by ultraviolet radiation. If life can persist in the Atacama, the thinking goes, perhaps it can persist somewhere in the red dust of another planet. And then, once every several years, or once every several decades, something breaks the pattern, a moisture conveyor belt, a high-altitude atmospheric river finds its way over the Andes. A shift in the ocean currents warms the coastal water slightly. A low-pressure system wanders further south than usual, and rain falls on the Atacama. Not much, perhaps an inch, perhaps 2 inches in a single day, which sounds almost laughably small by the standards of any rainy climate, but represents multiple years of normal precipitation delivered in hours. For the Atacama, an inch of rain is an event, a disruption, something almost geological in its significance. When it happens, the desert responds in 2 very different ways, and both of them are extraordinary for the ancient microbial communities in the deep soil, organisms that have spent millions of years evolving in absolute dryness. Sudden rain can actually be catastrophic. When researchers studied the aftermath of rare rain events in the Atacama, they found not a bloom of life, but a collapse. The microbes, so exquisitely adapted to the complete absence of liquid water, are in some ways damaged by its arrival. Osmotic shock, the sudden rush of water into cells adapted to extreme dryness, can rupture membranes and disrupt the chemical balance that the organisms have spent their entire evolutionary history maintaining. In studies following rainfall events in 2015 and 2017, nearly 3/4 of the measurable microbial species in affected soils disappeared afterward. Rain, for some of the oldest and most specialized life on Earth, is not relief. It is a catastrophe. But for the seeds, it is everything. Beneath the Atacama's dry surface, and beneath the surfaces of other great deserts, including the Sahara, the Namib, the Mojave, and Death Valley in California, lies a hidden inheritance, a seed bank. Millions upon millions of tiny seeds, some of them decades old, some of them perhaps a century old, lying in complete dormancy in the dry soil. They are not dead. They are waiting. Desert wildflower seeds have evolved a remarkable form of patience. In their dormant state, they rise at all. Their internal clocks slow to almost nothing. They have protective coatings that resist the mild occasional moisture of a light shower, preventing them from germinating when conditions are not quite right. When a single light rain might be followed immediately by heat and drought that would kill any seedling, the coating in some species requires a specific threshold of moisture to dissolve, not a light drizzle. Actual rain, sustained and substantial, soaking the soil to a meaningful depth. When that rain comes, the seeds respond. They germinate. They push stems upward through the cooling soil. They open leaves. And then, in a window of weeks, sometimes only 2 or 3 weeks, they race through their entire life cycle, growing, flowering, being pollinated, setting seed, dying, all of it completed before the sun returns, and the heat builds, and the surface dries again. And the result, when the conditions are right, when the rain was heavy enough and arrived at the right time of year, and was followed by mild temperatures and calm winds, is the phenomenon called a superbloom. The desert turns. Overnight, almost. Fields that were bare, cracked, dusty ground become carpeted in flowers. Vast sweeps of yellow and orange and purple and white stretching to the horizon, individual species that have not been seen flowering in that location for years, or sometimes decades, suddenly present in their tens of thousands. Pollinators that seemed absent, bees and butterflies and beetles that somehow persisted through the dry years, appear from nowhere and begin their frantic work. A superbloom is a kind of compressed time. All the flowering that could not happen across a decade of dry years happening at once. In a few extraordinary weeks, because the rain finally came. Death Valley National Park in California, one of the hottest and driest places in North America, receiving on average barely 2 inches of rain a year, experienced one of its most spectacular superblooms in a decade in early 2026, after an unusually wet autumn, and winter delivered more than 2.5 inches of rain. The valley floor, which for most years shows only a sparse scattering of plants, filled with gold and lavender and white, visible from miles away, drawing visitors from across the country to stand in what looks like a painting and is somehow perfectly real seeds that germinated in that super bloom may have parents that last flowered before any of those visitors were born. The waiting built into desert seeds is one of the most patient strategies in all of biology. They do not struggle against drought. They do not try to persist through impossible conditions. They simply stop. They become almost nothing. They wait in the dark for however long the dark lasts, certain in some wordless biological way that the rain will come again eventually, that the conditions will be right again someday, that the window will open, and when it does, they do not hesitate. This is the desert's relationship with rain, not the daily familiarity of a rainforest, not the reliable seasonal cycle of a temperate meadow, but something rarer and more dramatic, rain as a once-in-a-generation event. Rain as the thing the entire landscape has been holding itself in readiness for. Rain as the word that wakes everything that has been sleeping. There is something in the desert's patience that feels relevant to the long, slow movements of a restful night. The way sleep does not rush toward you when you pursue it, but arrives, sometimes after what feels like a long, dry wait, when the conditions finally align, the body cooling, the breath slowing, the thoughts becoming less insistent, the windows of wakefulness narrowing gradually until they close. Not sleep seized, sleep arrived, like rain on the desert. After a long, patient, trusting wait, everything that has been dormant and still and waiting now beginning, very gently to open. Everything we have discussed so far, the water cycle, the clouds, the drops, the fronts, and the monsoons, and the fog, and the desert blooms. All of it belongs to one small, blue, improbable planet. Earth's rain is not the only rain in the universe. It is not even the only rain in our own solar system. Across the planets and moons and distant exoplanets that fill the observable cosmos, precipitation of one kind or another is surprisingly common. the same physics that lifts water from our oceans and returns it as rain, evaporation, condensation, droplet formation, gravitational fall, operates wherever there is an atmosphere and a substance volatile enough to cycle through it, but the substances themselves are almost unimaginably different. Let us begin close to home. Let us begin with our nearest planetary neighbor and one of the stranger weather systems in the solar system. Venus. From a distance, Venus appears calm. A bright, featureless disk, perpetually cloud-covered, reflecting more sunlight than any other planet. Those clouds are thick and continuous, layered across the entire planet from pole to pole, never breaking, never revealing the surface beneath. But those clouds are not water. They are concentrated sulfuric acid. Sulfuric acid forms in the upper Venusian atmosphere through a series of chemical reactions involving sulfur dioxide from the planet's volcanoes, water vapor, and the intense ultraviolet light of the sun. The resulting droplets, tiny, highly corrosive, capable of dissolving metal and destroying organic tissue on contact, form clouds that look, from space, something like the white clouds of Earth, and from these clouds, sulfuric acid rain falls. It falls through the cloud layers. It descends through the thick Venusian atmosphere. And then, about 25 kilometers above the surface, it evaporates. Venus is too hot for anything to reach the ground. The surface temperature is around 465 degrees Celsius, hot enough to melt lead, hot enough that any raindrop of any substance simply vaporizes before it completes its journey. The sulfuric acid rises back up as vapor, recondenses into the clouds, falls again, evaporates again. An eternal cycle of precipitation that never arrives. Rain that falls forever and touches nothing. The planet rains perpetually and receives nothing. There is something almost poetic in that, in a melancholy sort of way. Moving outward through the solar system, past Mars, whose thin atmosphere occasionally produces carbon dioxide snow on its poles, but not meaningful liquid rainfall. We reach the outer planets and their extraordinary moons, Saturn has a moon called Titan. And Titan is, in many ways, the most Earth-like place in the solar system. Not because it is warm or welcoming or anything like our home planet in its details, but because it has a complete and active weather cycle. It has clouds. It has rain. It has rivers and lakes and a vast inland sea. It has a thick, hazy orange atmosphere dense enough to require a parachute to land through. The difference is in the substance. On Titan, the role that water plays on Earth is played entirely by methane. Titan is so cold, its surface temperature hovers around minus 179 degrees Celsius. That methane exists there in all three states that water exists in here as a gas in the atmosphere, as a liquid in rivers and lakes, and the great sea called Ligeia Mare in the northern polar region, and under certain conditions in the upper atmosphere as ice clouds. Methane evaporates from Titan's seas. It rises into the cold atmosphere. It condenses into clouds of methane ice and droplets, and it falls as methane rain, heavy, slow drops of liquid natural gas drifting down through the orange haze toward a landscape of dark hydrocarbon pebbles and methane-carved river valleys. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, observed Titan's surface in extraordinary detail and found all the features you would expect from a world with an active rain cycle, drainage networks, alluvial fans where rivers spread their sediment at their mouths, shorelines of lakes that rise and fall with the seasons. The methane cycle on Titan runs slowly. Titan's year is as long as Saturn's, about 29 Earth years, but it runs the same fundamental choreography as Earth's water cycle, performed in a different substance, at a different temperature, on a moon 600 million miles from the sun. There is something calming about this, the knowledge that rain, the same essential process of evaporation and condensation and precipitation and collection, happens somewhere as different as the frigid orange surface of a distant moon that the universe finds ways to cycle its liquids wherever conditions allow. That rain, in some form, is not unique to us. Neptune, in the gas giant outer solar system, is believed to produce a form of precipitation that is perhaps the strangest of all in Neptune's deep interior, and possibly in the interior of Uranus as well. Pressures and temperatures are so extreme that carbon-bearing molecules in the atmosphere are compressed and heated until the carbon atoms separate out, and those carbon atoms, under sufficient pressure, may crystallize. They may, in other words, form diamonds. Diamond rain. Diamonds forming from compressed carbon deep inside a gas giant, sinking through the layers of the planet's interior under their own weight, accumulating perhaps in a layer of liquid diamond somewhere deep in the planetary interior. This has not been directly observed. Neptune's interior is not easily accessible, but experiments recreating the pressures and temperatures involved have produced diamond formation, and the physics appears to support the idea. Neptune may be raining diamonds right now. Quietly, deep inside a cold blue gas, giant 4.5 billion kilometers from the sun. And then there are the exoplanets, the planets orbiting other stars, many of them so alien and so hostile that the word planet barely seems adequate. Consider was P-76 billion, a world about 640 light years from Earth, in the constellation Pisces, a planet roughly the mass of Jupiter, orbiting so close to its star that its year lasts less than 2 Earth days. A planet tidally locked, one side facing its star forever, one side facing away into permanent night, with no rotation to distribute the heat. The day side of was P-76 billion reaches temperatures of approximately 2,400 degrees Celsius. Not 200, 2,400. Hot enough to vaporize iron at those temperatures. Iron in the atmosphere does not form solid rock. It becomes iron vapor, swept up into the scorching dayside atmosphere and carried by ferocious winds toward the cooler night side. on the night side, where the temperature drops to a relatively mild 1500 degrees Celsius, the iron vapor cools. It condenses. It falls. Was P-76 billion rains molten iron on its night side at winds of approximately 18,000 kilometers per hour. There is another world, HD 189,733 billion, a deep cobalt blue in color, the blue coming not from ocean or sky, but from tiny particles of silica in its atmosphere, silicate particles. Glass. The upper atmosphere of this planet is hot enough to vaporize rock and cool enough in certain layers to condense that rock vapor into tiny glass particles, which then fall as glass rain, or rather glass hail, sideways through the air at speeds exceeding 8,000 kilometers per hour, driven by winds that circle the entire planet in hours. Rain of glass, rain of iron, rain of methane, rain of sulfuric acid that falls forever and arrives nowhere. Diamond rain in the dark interior of cold blue giants. These are the forms that precipitation takes when the same physical principles operate in different substances under different conditions around different stars. And in the middle of all of this vast inventory of alien downpours, this catalog of exotic weather across impossible worlds, there is Earth, quiet, temperate Earth, where the rain is made of water, where it falls at a few meters per second, not thousands of kilometers per hour, where it is cool but not cryogenic, where it nourishes things rather than vaporizing them, where it gathers in pools and rivers and reservoirs, and is drunk by creatures that have evolved over billions of years in the expectation of its arrival. Water rain on an ordinary evening, falling on ordinary ground, the most unremarkable thing in the universe, perhaps. And also, when you hold it against everything else that falls out there in the dark, one of the most extraordinary. Let that softness settle around you. This particular rain, this particular planet, these particular drops finding their way to the ground in the gentlest possible way, after the longest possible journey through the strangest possible universe. You are here for it, and it is here for you. Every river begins with rain. It is easy to forget this standing beside a great river, the Mississippi, the Amazon, the Nile, the Ganges, watching the enormous, steady, muscular movement of all that water heading toward the sea. The scale of it seems to suggest something permanent and geological, something that has always been there and always will be, independent of weather and sky. But pull the rain away, remove the precipitation from the watershed that feeds it, and the river slowly empties. The great brown Mississippi would thin to a trickle. The Amazon would contract. The Nile, whose headwaters draw from the monsoon rains of East Africa and the highlands of Ethiopia, would fall. Every river is the accumulated memory of rain that fell somewhere upstream. All of it gathered, all of it pooling, all of it finding its way downhill, following the simplest and most ancient of physical laws. Water runs downhill. That is the whole story in its shortest form. Rain falls on high ground. Gravity pulls it downward. It follows the contours of the land, seeking the lowest available path, joining with other water flowing in the same direction, building from a trickle into a stream, and from a stream into a river, all the way to the sea. The land that drains to a single river is called its watershed or catchment. Every hillside, every meadow, every forest floor, every road and rooftop within the watershed is part of the system. When rain falls anywhere within the watershed, even hundreds of miles from the river itself, some portion of that rain will eventually reach the river. It may soak into the ground first and travel slowly through the soil for weeks or months before emerging as a spring that feeds a small tributary. It may run off the surface immediately in a fast-moving rivulet that joins a stream within hours. But the watershed collects it all eventually and sends it to the same destination. This is why rivers rise after rain that fell far away. A river in the flat lowlands can flood days after a storm passed through the mountains at its source. 100 miles distant, the the water working its way down the watershed, concentrating in the river's channel, arriving with a delay that can catch the unwary completely by surprise. The river and its storm are not in the same place. They are connected across distance and time by the slow, inexorable logic of water running downhill. A river, if you look at it from above, from a satellite or an aircraft, has a shape that is immediately recognizable. The main channel, the trunk, with its tributaries branching off it like the branches of a tree. And those tributaries have smaller tributaries, and those have smaller ones still, until you reach the tiniest rills and rivulets at the very edge of the watershed. Threads of water moving through grass after rain. The whole system is a tree. It is called the dendritic drainage pattern, from the Greek word for tree. And like a tree, it is fractal. The same branching structure repeats at every scale, from the smallest stream to the widest river. Rain falls on the leaves of the tree. Gravity brings it to the trunk. The trunk carries it to the sea. But before it reaches the sea, the river does something extraordinary to the land it travels through. It shapes it. A river is not merely a passive conduit for water. It is one of the most powerful geological forces on the surface of the earth. Moving water carries energy, and that energy is applied continuously and patiently to the bed and banks of the river's channel. It erodes. It picks up grains of sand, particles of silt, fragments of gravel, even boulders in the most powerful floods, and carries them downstream. Over thousands of years, this carving deepens valleys. Over millions of years, it can cut canyons a mile deep into solid rock. The Colorado River through the Grand Canyon is perhaps the most dramatic example. But every river valley on Earth is the work of water moving over time, carrying away what the rain brought to it, grain by grain, flood by flood. The river remembers every storm that ever fed it. The valley it carved is the accumulated record of all the rain that has fallen in its watershed across geological time. And wherever the river slows, where it widens into its lower reaches and loses the energy to carry what it has been transporting, deposits. It lays down its sediment. It builds flat, fertile floodplains from the material it has collected in its upper reaches and carried patiently to the lowlands. These floodplains are among the most fertile soils on Earth, and this is why, when the first human beings began to leave behind the nomadic life of the hunter-gatherer and settle in permanent communities, to plant crops, to build houses, to develop language and law and art, they did it beside rivers, not beside mountains or coastlines or open grasslands, but beside rivers. The Tigris and the Euphrates in Mesopotamia, the Nile in Egypt, the Indus in what is now Pakistan, the Yellow River in China, 4 great rivers, 4 great civilizations, each one built on the same foundation. The annual floods that brought new silt to the floodplain, renewing its fertility. The reliable supply of drinking water, the route of transport and communication that the river itself provided, connecting upstream communities to downstream ones. The rain that fell in the mountains far upstream, concentrated and delivered by the river to the flat, warm, fertile lowlands, made civilization possible, not as a metaphor. Literally, without river-delivered rain, without watersheds concentrating precipitation and delivering it reliably to the lowlands, the first cities could not have been built. The first surpluses of grain could not have been grown. The first complex societies could not have emerged. Every city that has ever existed was downstream of rain. There is a particular sound that rivers make, not uniform, not constant in pitch or volume, but endlessly variable depending on the depth, the speed, the bed material, the obstacles. A deep, slow river in its lower reaches moves almost silently. A low, continuous, barely audible sigh, the water pressing against its banks with no urgency. A young mountain river rushing over boulders is all percussion and spray, high, bright, constantly shifting sound. The water in a hurry, not yet having learned the lower river's patience. The sound of rivers has been one of the most universally calming sounds in human experience for as long as humans have been near rivers. which is to say, always. We evolved beside rivers. We drank from them, and washed in them, and fished in them, and crossed them, and buried our dead near them. The sound of moving water, that particular continuous, non-repeating, non-threatening sound, is as deep in us as anything. It is no coincidence that the recordings most often used to aid sleep are rain sounds and river sounds and ocean sounds. 3 variations on the same theme. 3 forms of the same water, doing the same thing it has always done, making the same sounds it has always made, saying the same thing it has always said to the part of us that is still sitting by a river in the dark after a long day, listening to the water pass. The rain falls on the high ground. It finds its way into the small streams. The small streams find their way into the tributaries. The tributaries find the river, and the river moves steadily in its ancient and unhurried way through the valley it made, through the civilization that grew beside it, toward the sea it has always been returning to. All of it has been in motion since before there were eyes to watch it. All of it will be in motion long after. And for right now, in this particular moment, you can simply be beside the river in the dark, listening to it pass. It does not need you to guide it. It knows exactly where it is going, and the sound it makes on its way, there is one of the oldest lullabies there is. You can smell rain before it arrives. On a warm afternoon in late summer, when the air has been dry for days, and the ground is pale and dusty, and the sky to the west has begun to darken with the first suggestion of approaching cloud, before any drop has fallen, before the temperature has shifted, before the first distant rumble has crossed the horizon, there is a smell, something clean and faintly mineral and deeply, almost disturbingly familiar. Something that bypasses thought entirely and lands directly in the part of the brain where memory and feeling live. You have smelled it your whole life. You know exactly what it means. Rain is coming. That smell has a name. It was given to it in 1964 by 2 Australian researchers, Isabel Joy Baer and Roderick Grant Thomas, who published a paper in the journal Nature describing the distinctive scent released when rain falls on dry earth. They called it Petrichor, from the Greek Petra, meaning stone, and ichor, the fluid said to flow in the veins of the gods. The essence of stone, the blood of the earth, made briefly airborne by the first drops of rain. It is one of the most evocative names in all of science, and the chemistry behind it is, appropriately, beautiful. Petrichor is not a single compound. It is a blend, a layered fragrance assembled from several different sources, each contributing its own note to the whole. The first and most significant contributor is a molecule called geosmin. It is produced by soil-dwelling bacteria called actinomycetes, particularly a genus called streptomyces, the same family of microorganisms responsible for producing the antibiotic streptomycin. These bacteria live in almost every soil on Earth, in gardens and forests and deserts and the banks of rivers, quietly decomposing dead plant matter, breaking it down into the nutrients that feed new growth. During dry periods, when the soil dries out and the bacteria's activity slows, geosmin accumulates in the soil. The bacteria produce it as part of their life cycle, secreting it during sporulation, when they form the hardy, desiccation-resistant spores that will carry their genetic material through the drought. When rain arrives, when the first drops hit the dry soil, the impact aerosolizes those spores and their volatile compounds, launching tiny droplets into the air. The geosmin rides these droplets into the air column above the ground, dispersing upward and outward in the turbulent air just above a freshly wetted surface. And then we breathe it in. The human nose is extraordinarily sensitive to geosmin. Extraordinarily sensitive is, if anything, an understatement. We can detect it at concentrations as low as 5 parts per trillion, 5 molecules of geosmin for every trillion molecules of air. To put that in perspective, if you dissolved a single drop of geosmin into an Olympic swimming pool of water, you could still detect the flavor. The olfactory receptors in the human nose respond to geosmin with a sensitivity that has no obvious parallel among common environmental compounds. acutely sensitive to the smell of rain-wetted earth, the most compelling hypothesis is evolutionary. For most of human prehistory, finding water was one of the most critical challenges of daily survival. In dry environments, the savanna and semi-arid landscapes, where much of early human evolution appears to have taken place, rain meant water to drink, plants to eat, animals to hunt. The smell of rain on dry ground was a signal of extraordinary importance. The individuals who could detect that signal earliest and follow it most reliably, who smelled the first drops half a mile away and moved toward them, would have had a survival advantage. The sensitivity may be, in other words, a gift from our ancestors, a piece of ancient navigation equipment still installed in the nose, still working perfectly, still sending the same urgent, slightly thrilling signal it sent 100,000 years ago. Rain, water, go. But geosmin is only one ingredient in Petrichor. The second comes from plants. During dry spells, many plants, particularly shrubs and low-growing flowering plants in semi-arid regions, produce aromatic oils that they secrete into the soil and onto rocks around them. The exact purpose of these oils is debated, but one leading hypothesis is that they act as a kind of chemical lawn, compounds that suppress the germination of competing plants nearby during dry conditions. When there is not enough water to support multiple plants in a small area, these oils accumulate in the thin mineral layer of soil and stone during dry weather. And when rain arrives, they are released. The water displaces them from the surfaces they cling to, and they volatilize. They become airborne, contributing a warm, resinous, slightly herbal note to the Petrichor blend. It is partly this component that gives Petrichor its slightly dusty, slightly green, slightly ancient quality. The smell of stone and dry earth and something living that has been waiting in the rocks. The third contributor is ozone. Before a thunderstorm, lightning in the upper atmosphere splits oxygen molecules, which then reassemble into ozone. 3 oxygen atoms bonded together rather than the usual 2. ozone has a sharp, clean, faintly metallic smell. It drifts downward in the airflow ahead of a storm, arriving at ground level before the rain, adding its clean electric note to the scent of geosmin and plant oils. It is partly this ozone component that makes pre-storm air smell so electric and clean. The ionized, ozone-tinged air of an approaching thunderstorm is what many people describe when they say they can smell rain coming. They are smelling lightning before they see it. The full Petrichor experience, then, is a chord. Geosmin from the bacteria in the awakened soil, earthy, deep, familiar. Plant oils released from stone and dry ground, warm, herbal, resinous, ozone from distant lightning, sharp, clean, electric. Each note arriving at slightly different times. The ozone first, then the geosmin as the drops hit, then the plant oils as the rain soaks in. The whole fragrance shifting and developing over the first minutes of a rainfall. The way the opening notes of a piece of music give way to the fuller theme, and then, if it rains long enough, if the ground becomes wet and saturated, and the bacteria's spores are washed down into the soil rather than aerosolized, the smell changes. It softens. The sharp petrichor of the first drops becomes something more muted and green. The smell of wet grass and soaked earth and rain still falling. The drama of the first scent gives way to the steady, ordinary, completely comfortable smell of a rainy day in progress. Perfumers have spent decades trying to capture petrichor. Some have come close. There are fragrances that carry recognizable notes of geosmin that conjure the smell of rain in a convincing way, but none of them quite replicate the real thing. Perhaps because the real thing is not just a chemical formula. It is a context. It is warm, dry air suddenly changed. It is the particular quality of attention that arrives when something you have been waiting for, without quite knowing it, finally shows up. The smell is inseparable from its timing. Petrichor, bottled and applied on a dry afternoon, is just a scent. Petrichor arriving on the actual first drops of actual rain is something else entirely. There is also something worth noting about what geosmin smells like to other creatures. Researchers studying Streptomyces bacteria discovered in 2020 that the geosmin released by these soil bacteria acts as a navigation signal for tiny soil-dwelling arthropods called springtails. The springtails are attracted to the geosmin smell, find the bacteria, feed on them, and in doing so pick up bacterial spores on their bodies and carry them to new locations. The smell of rain is, in part, bacteria advertising themselves to the creatures that will spread their spores. Petrichor is bacterial perfume, deployed at exactly the moment, the first rain, when the dispersal opportunity is greatest. So when you smell rain, when that wave of clean, earthy, electric scent reaches you before the first drop falls, you are smelling bacteria waking up. You are smelling plants releasing their dry season chemistry. You are smelling lightning from miles away. You are smelling a whole community of soil life responding to the arrival of water. And somewhere in your ancient nervous system, something responds to that smell with a recognition that goes deeper than memory. Water here, now. Everything is going to be all right. Breathe that in now, if you can find it, that imagined smell of rain on dry ground, or wet pavement, or a garden after the first summer downpour. The smell your body knows the way it knows warmth and rest, and the particular quality of safety that arrives when you are indoors and it is raining outside. Let it settle into you the way rain settles into the ground. Snow is rain that took its time. Both begin the same way, as water vapor rising into a cold atmosphere, condensing around a microscopic particle, building into a droplet in the dark interior of a cloud. But where a raindrop forms in liquid water and falls as liquid water, a snowflake forms in ice and grows in ice and falls as ice and arrives at the ground still in that same crystalline state, provided the air it passes through on the way down is cold enough to keep it frozen. The difference between rain and snow is largely a matter of a few degrees. A few degrees of temperature in the cloud. A few few degrees in the air between the cloud and the ground, the same water, the same cloud, the same gray sky above the same landscape, and the choice between a rainy afternoon and a snowy one comes down to whether the thermometer sits just above or just below the freezing point. But within those few degrees, something extraordinary happens. Ice is not simply frozen water. It is a crystal, and crystals have structure. The atoms that make them up arranged in precise, repeating geometrical patterns determined by the physics of their chemical bonds. In ice, water molecules, each one an oxygen atom bonded to two hydrogen atoms, arrange themselves in a hexagonal lattice, six-sided, symmetrical. The same geometry arising from the same molecular angles. Every time water freezes into ice, this hexagonal structure is the reason every snowflake has six sides. Not four, not eight, not five. Always six. The six-fold symmetry is not a coincidence or an aesthetic preference of nature. It is the direct, inevitable consequence of the angle between atoms in a water molecule. 104 degrees. That angle, repeated across billions upon billions of water molecules as they lock together in the growing crystal, always produces the same fundamental hexagonal shape. A snowflake begins its life as a single ice crystal, barely larger than the period at the end of a sentence. A tiny hexagonal prism, perfectly clear, forming around a speck of dust or pollen or a mineral particle in the cold upper atmosphere. For a while, it grows simply. Flat hexagonal plates or tiny columns shaped like pencils, depending on the temperature. Simple shapes, modest shapes. But as it falls, it enters different layers of the atmosphere, slightly different temperatures, slightly different humidities, and these changing conditions change how it grows. At certain temperatures and humidity levels, the crystal grows faster at its corners than its flat faces, and the corners sprout branches. Those branches grow and sprout their own side branches, which sprout their own, the whole structure becoming progressively more elaborate as the crystal descends through a column of air that is constantly, subtly changing the resulting shape. The classic stellar dendrite, the lacy six-armed snowflake of Christmas cards and winter imagery, is the crystal's autobiography. Its shape is a record of every temperature and humidity change it experienced during its journey from cloud to ground. Every side branch, every tiny ridge on every arm is the imprint of a specific atmospheric condition at a specific moment in the crystal's fall. This is why no two snowflakes are alike, not because randomness intervenes, but because no two snowflakes follow exactly the same path through the atmosphere. Each crystal takes its own route, experiences its own sequence of temperatures and humidities, and records those experiences in its shape. The combinations of conditions are effectively infinite. A single snowflake may contain a quintillion water molecules, each placement affected by the conditions at that precise moment. So, the number of possible snowflake shapes is larger than the number of atoms in the observable universe. Every snowflake is a unique record, a tiny, intricate, temporary archive of the particular journey it took from cloud to ground. And then it lands and begins to metamorphose, and within hours or days has lost its individual form and merged into the snowpack, becoming part of something collective and vast. The snowpack. There is a tendency to think of snow as a kind of pause, a stopping of the water cycle, a winter freeze that holds everything in place until the thaw. But this is not quite right. The snowpack is not a pause. It is a reservoir, a slowly filling, slowly releasing store of water that mountain communities and river systems and entire ecosystems depend on. In the western United States, the snowpack of the Sierra Nevada and the Rocky Mountains holds the majority of the region's annual water supply. The snow that falls in December and January and February accumulates across the mountain ranges, layer by layer, compressing into a dense mass. And then, as the temperatures rise in spring and early summer, it melts, not all at once, but gradually, steadily, sending cold meltwater down through the soil and into streams and rivers for weeks and months. A river fed by snowmelt runs clear and cold and steady into June and July, long after the last rain fell. The snowpack is a release mechanism for the year's precipitation. It takes the concentrated water of winter storms and distributes it through the dry months that follow. Without it, the rivers that feed farmland and cities in the American West would run high in winter and dry in summer, and the entire agricultural and urban infrastructure built around their reliability would collapse. Mountain snowpack has been called the West's largest natural reservoir, and it is a reservoir that is free to build and free to maintain, and has been operating quietly and reliably for millions of years. Snow changes a landscape the way almost nothing else can. Rain wets things. Snow covers them. A heavy snowfall rearranges the visual world completely, eliminates the distinction between ground and path, between hedge and ditch, between garden and road. Everything that was differentiated and distinct becomes part of a single, white, unbroken surface. The world simplified, rounded, quieted. Sound behaves differently in snow. The density of fresh snow, its many tiny trapped air pockets between the ice crystals, makes it an excellent acoustic absorber. Sound waves entering a snowfield are caught by the irregular surfaces between crystals and converted into tiny vibrations rather than reflecting back. A landscape after heavy snowfall is acoustically softer than normal. Sounds that would carry across an open field in summer are absorbed within a few meters. The world feels more interior, more muffled, more private. The particular quality of silence after snowfall, that soft, padded, resonance-free silence, is one of the most distinctive environmental sounds there is. Absence of sound as sound. Presence of quiet as a positive, palpable thing. And snow, like rain, has its own smell. Or rather, the absence of smell. Fresh snow washes the air of particulates and aerosols that normally carry scent. The air after snowfall is often the cleanest, most odorless air of the year. Breathing it feels like breathing something that has been freshly made. A clarity that is almost physical. Snow falls more slowly than rain, much more slowly. A raindrop falls at somewhere between 2 and 9 meters per second, depending on its size. A snowflake, with its enormous surface area relative to its mass, encounters so much air resistance that it falls at less than a meter per second, sometimes far less. It drifts rather than falls. It has time to be caught by the smallest breath of wind, shifted sideways, turned, carried a long horizontal distance before finally settling. Each flake visible, each one traceable with the eye for its final few meters of descent. This slowness is part of what makes snowfall beautiful in a way that rain is not. Snow is patient precipitation. It gives you time to see it happening. There is, in the end, a deep kinship between rain and snow that is easy to forget when they feel so different. The same cloud, the same water vapor, the same condensation nuclei, the same impulse of the sky to return to the earth what the earth gave it. Rain comes quickly and warmly and with sound. Snow comes slowly and silently, taking its time, recording its journey in its shape, covering the world in something that will melt slowly and return to the rivers in its own time. Both are gifts. Both are the sky finding its way back home. And both, on the right night, from the right window, with the right quality of soft attention, can dissolve the boundary between being awake and being asleep. Let the snow fall slowly behind your closed eyes if it wants to. Each flake finding its own path down. No two the same. All of them arriving eventually in the same quiet white. Before there was writing, there was planting. And before there was planting, there was the patient observation of rain. Somewhere in the arc of human history, not a single moment, not a single place, but a slow unfolding across several regions of the world between 10,000 and 12,000 years ago. People noticed something, that the seeds of wild grasses, scattered by wind and animal, and the plants themselves, germinated after rain, that the flat, wet margins of rivers and lakes, where seasonal floodwaters deposited rich sediment and then retreated, produced the most abundant wild growth. That rain, soil, and seed, given time, produced food. And from that observation, everything followed. Agriculture, the deliberate cultivation of plants for food, is the foundation of every civilization that has ever existed. Every city, every army, every library, every cathedral, every work of art, every technology from the wheel to the microprocessor rests on the same foundation. The ability of a relatively small number of people to grow enough food to feed many others, freeing some portion of the population from the work of constant foraging. And that ability rests at its most fundamental level on rain, not always directly. The earliest large-scale agriculture in Mesopotamia, in the valley between the Tigris and Euphrates rivers, where the first cities were built, depended not on rainfall, but on irrigation. The rainfall in that region was too sparse and too unpredictable for reliable dryland farming. But the rivers themselves were fed by rain, falling on mountains far to the north, delivered to the lowlands by the same logic of watersheds and river systems we explored in an earlier section. The Sumerians, around 6,000 years before the Common Era, built an elaborate network of irrigation canals that diverted river water onto their fields. Dikes and sluice gates and channels, maintained by organized labor, administered by the first institutions that we would recognize as government. The canal was the agricultural technology, but behind the canal was a river, and behind the river was rain. In Egypt, the relationship was even more direct and visible. The Nile flooded every year, predictably, reliably, in late summer. Because monsoon rains thousands of miles to the south, in the Ethiopian highlands, filled the river's headwaters and sent a pulse of water north across the desert. Egyptian farmers did not need to fully understand the hydrology. They knew that the flood would come, that it would deposit rich silt across their fields, and that that if they planted after the floodwaters retreated, the soil would be moist and fertile, and the crop would grow. Their calendar was organized around the Nile's flood. Their gods included a god of the flood and a god of fertility and a god of grain, and these were among the most important gods in their pantheon. The entire theological architecture of ancient Egypt was, in its practical foundation, a system of beliefs organized around the management of water and the production of food. Rain delivered by river was the axis around which civilization rotated. In other parts of the world, in the highlands of the Levant, in parts of sub-Saharan Africa, in the ancient farming communities of North Africa's Green Sahara, before the climate shifted, agriculture depended on rain directly. Dryland farming. No river, no canal. Just soil, seed, and sky. These farmers developed an intimate understanding of the rain that any modern meteorologist would recognize as sophisticated empirical observation. They knew which seasons brought rain and which did not. They knew which soils held moisture longest and which drained too quickly. They knew that a late frost after spring rain could kill a crop, and that too much rain at harvest time could rot the grain before it was gathered. They knew the smells and the winds and the cloud formations that predicted rain. They read the sky the way we read a page, quickly, fluently, with an understanding accumulated over generations. This knowledge was precious. It was encoded in oral traditions, in stories and songs, and seasonal rituals designed to be remembered and passed down. The planting calendar, the prayers for rain, the harvest festivals, these were not merely cultural traditions. They were information systems, packages of practical agricultural knowledge wrapped in a form that a community could reliably transmit across centuries without writing. What rain does to a plant is something both simple and extraordinary. Water enters the plant through its roots, tiny hair-like root structures that extend through the soil, pressing between soil particles, absorbing moisture by osmosis. That water travels upward through the plant's vascular system, driven partly by the pressure of water in the roots, and partly by the evaporation of water from the leaves. The same evaporation that drives transpiration and contributes to the water cycle. The water carries dissolved nutrients from the soil into the plant's tissues. It provides the hydrogen atoms for photosynthesis, the process by which the plant captures energy from sunlight and stores it as sugar. Without water, photosynthesis stops. The stomata, the tiny pores on leaf surfaces through which gases and water vapor pass close to prevent further water loss. The plant enters a state of stress if the water deficit persists long enough. Cells begin to lose turgor pressure, the internal pressure that keeps plant tissues firm, and the plant wilts. If drought continues beyond a critical threshold, the damage becomes irreversible. The crop fails. Every farmer who has ever lived has known this sequence intimately. The watching for rain, the assessment of the soil, the decision of when the situation becomes critical, the helplessness of having done everything right and still watching a crop fail because the rain did not come in the week it needed to come. And yet, the relationship between rain and agriculture is not simply more rain equals better harvest. Too much rain is its own disaster. Waterlogged soils suffocate plant roots, which need air as well as water. Prolonged wet weather encourages fungal diseases, the blights and rusts and mildews that can destroy a field of otherwise healthy plants in days. Rain at harvest time softens grain and slows drying and invites rot. Rainfall distributed evenly through a growing season is worth far more than the same total amount delivered in 2 floods with dry periods between. What farmers need is not simply rain. They need the right rain at the right time in the right amounts. This is why weather forecasting, even in its crudest, most observational forms, has always been among the most practically important knowledge a community could possess. Long before barometers and satellites and numerical weather prediction models, farmers read cloud formations and wind direction and animal behavior, looking for patterns that might give them a few days' warning of what the sky was about to do. Their crops depended on that reading. Their family's survival depended on those crops. Today, on almost every cultivated acre of farmland on Earth, the relationship between rain and agriculture continues to play out in the same fundamental way it always has. Technology has added irrigation systems and satellite weather forecasts and drought-resistant crop varieties. But the plant still needs water. The soil still needs moisture. The farmer still watches the sky, and when rain falls on a field of young plants, a gentle, steady, soil-soaking rain in the right week of the growing season, it is still one of the most genuinely welcome events that a farming community can experience, not merely economically welcome, emotionally welcome. The particular kind of relief that humans have been feeling for 12,000 years, standing at the edge of a field in the rain, knowing that this particular anxiety, the anxiety of the dry spell that went on a few days too long, is over. The ground is drinking. The roots are finding what they needed. Something is going to grow. There is a quiet miracle in that. So quiet, so ordinary, so repeated across every culture, in every continent, across every century of human history, that it requires the deliberate effort of attention to see it as the miracle it is. Rain falls, soil absorbs it, seeds wake, roots grow, leaves open. The sun does its part, and the rain does its part, and the patient, ancient, unhurried process of a plant becoming food begins again, as it has always begun, as it will always begin after the rain. Before the rain, there are clouds, always clouds. Every drop of rain that has ever fallen on this planet began its final journey inside a cloud. The cloud is the factory, the waiting room, the decision-making place where the atmosphere makes up its mind about what form to deliver its water in, and when. To understand rain fully, you have to spend some time with the clouds that produce it, to look at them properly, to know their names and their natures, and the particular message each one carries about what the sky is thinking, which makes it all the more surprising, perhaps, that clouds were not formally named until the year 1802. The man who named them was a London pharmacist and amateur scientist named Luke Howard. He was 29 years old when he stood up before a small gathering called the Askesian Society and delivered a paper called On the Modifications of Clouds. In it, he proposed a classification system for the forms clouds take, a taxonomy, like the one the botanist Carl Linnaeus had devised for living organisms, using Latin names to describe each type precisely and universally. Howard identified 3 fundamental forms: cirrus, from the Latin for a curl of hair, the high, wispy, fibrous clouds that streak the upper sky like brush strokes, made entirely of ice crystals, cumulus, from the Latin for heap, the rounded, piled, cotton wool clouds of fair weather, flat-bottomed and dome-shaped, familiar to anyone who has ever watched clouds on a summer afternoon, and stratus, from the Latin for layer, the wide, flat, horizontal sheets of gray that drape across the sky and reduce a bright day to a dim, diffuse, textureless gray without quite deciding to rain. And then to these 3 he added a 4th, nimbus, from the Latin for rain cloud, not a shape but a condition, the designation added to any cloud that had decided to let go of its water. These 4 roots, cirrus, cumulus, stratus, nimbus, are the basis of every cloud name in use today. The World Meteorological Organization currently recognizes 10 main cloud genera, all of them assembled from Howard's original 4 building blocks: cumulonimbus, nimbostratus, altostratus, stratocumulus, cirrostratus, cirrocumulus. Every cloud name is a description of what it looks like and what it might do, encoded in 2 Latin syllables that Howard chose more than 200 years ago, standing at a window in London, watching the sky with the particular quality of attention that turns observation into understanding. Howard's classification was celebrated by more than just meteorologists. The German poet Goethe, who had been corresponding with Howard and had received a copy of his cloud classification, was so moved by the achievement of giving names to something as transient and shifting as a cloud that he wrote 4 poems in Howard's honor, one for each of the cloud types. The idea that the formless and ephemeral could be named without being diminished, that classification could be a form of poetry rather than a reduction, delighted him. To name a cloud is to notice it, and noticing clouds is one of the quiet pleasures of a life lived with some portion of attention directed upward. Let us take a slow journey through the cloud atlas. High in the atmosphere, at altitudes of 5 to 12 kilometers or more, where the temperature is well below freezing, and the air is thin and cold, are the high clouds, cirrus, those white, fibrous streaks that seem drawn by a fine brush across an otherwise clear blue sky, are made entirely of ice crystals, falling and drifting through upper level winds, painting the sky with long, curved lines that meteorologists call mare's tails. Cirrus clouds are often beautiful. They are sometimes the first sign of an approaching weather system, a warm front sending its thin advance guard of ice crystal cloud ahead of itself, hours or days before the rain arrives below. Cirrostratus is a thin, milky veil of ice crystals spread so finely across the sky that the sun and moon can shine through it, but with a distinctive ring or halo around them. A circular arc of colored light caused by the refraction of sunlight through the hexagonal ice crystals. When you see a halo around the moon on a clear-seeming night, you are looking through cirrostratus cloud at thousands of ice crystals, each one bending the moonlight in exactly the same way, thousands of meters above you. At middle altitudes, roughly 2 to 7 kilometers, the alto clouds sit. Altostratus is a gray or blue-gray sheet, thick enough to blur the sun to a bright smear, not quite dark enough to rain heavily yet. When altostratus thickens and descends, it becomes nimbostratus, the gray, featureless, low overcast that produces the steady, persistent rain of frontal systems. Nimbostratus asks nothing dramatic of you. It simply settles over the sky and opens, quietly and without ceremony, and reigns for a long time. Lower in the sky, and often the most visually varied, are the low clouds and the vertically developed clouds. Cumulus, Howard's heaps form on sunny days when thermals of warm air rise from the heated ground, cool as they ascend, and condense into white rounded towers with flat bases marking the altitude at which condensation begins. Fairweather cumulus are small and scattered and move across the sky with a relaxed, almost leisurely quality. They are the clouds of good days. They do not intend to rain, but cumulus is dynamic. It grows on days when the instability of the atmosphere is sufficient, when the temperature decreases sharply with altitude, and rising air remains warmer than its surroundings all the way up. A small cumulus cloud can build in an hour into a towering cumulonimbus, the great vertical thunderstorm cloud, a structure that may rise 15 or 18 kilometers from its flat, dark base to its spreading, anvil-shaped top, which is formed when the cloud reaches the stratosphere, the stable layer above the troposphere, and cannot rise further. So it spreads sideways in the shape of a blacksmith's anvil. Inside a cumulonimbus is everything we discussed in earlier sections. The violent updrafts and downdrafts, the charge separation, the lightning and the thunder, the heavy rain and sometimes hail. The cumulonimbus is the most dramatic structure the atmosphere produces. It contains more energy than a nuclear weapon. It creates its own weather, and it began only an hour or two before its full development as a gentle, rounded white cloud drifting on a sunny afternoon. Stratocumulus, the low, gray, lumpy, layered clouds that cover much of the world's surface on any given day, are the most common cloud type on Earth. Not dramatic, not especially beautiful, not usually producing more than light rain or drizzle, but persistent and prevalent and strangely comforting in their ordinariness. The gray blanket that covers a cool, quiet day and makes the light soft and even. Stratocumulus is the default setting of the sky across much of the temperate world for much of the year. And then there are the clouds that appear for special reasons. Lenticular clouds, smooth, disc-shaped clouds that form in the wave of air flowing over a mountain peak, hovering over the summit like enormous, perfectly shaped lenses, sometimes stacked in piles. They do not move with the wind because they are not moving through the air. They are constantly forming on the upwind side and evaporating on the downwind side. A standing wave made visible from a distance. They look so geometric and so still in a moving sky that they have, throughout history, been misidentified as something else entirely. Mammatus clouds, the strange, downward-pointing pouches that hang beneath cumulonimbus anvils after a severe thunderstorm. The sky suddenly looking as if the underside of the cloud has grown organs, bulging in pendulous clusters across a wide area. They are beautiful in an unsettling way, a reminder that the sky can do things with light and water that nothing in ordinary experience prepares you for. Clouds are impermanent. This is fundamental to their nature. They form in minutes and dissolve in minutes. The cloud you are looking at has not been there long and will not be there long. It is a temporary structure, maintained only by the continuous arrival of new moist air at its base and the continuous evaporation at its edges. Every cloud is a process, not a thing. And yet, while they last, while the light falls through them in the particular way it falls through each type, whether the sharp-edged white of a summer cumulus or the diffuse silver of a nimbostratus or the delicate tracery of cirrus, catching the last light of the day, they are among the most watched and most loved phenomena in the natural world. They have been watched for as long as there have been eyes to watch them. Luke Howard gave them names, but humans were looking long before that. And tonight, if you can, look up, even just with your memory, at whatever sky you carry with you, the clouds that are most familiar, the ones that mean something, that say something in a language you learned without being taught it. They are still forming somewhere above, carrying their water quietly, patiently, on their way somewhere. The water falling as rain tonight has fallen before. Not something like it. Not water of a similar age or origin. The same water. The same molecules. The same oxygen atoms. The same hydrogen atoms bonded together in the same configuration, that have been cycling through this planet's atmosphere and oceans and rivers and ice sheets and living tissues for longer than it is easy to comprehend. The hydrogen atoms in every water molecule on Earth were forged in the Big Bang more than 13 billion years ago. The oxygen atoms were made inside stars that burned and exploded billions of years before the sun existed. The molecules they formed together, 2 hydrogen, 1 oxygen, the most abundant molecule on the surface of this planet, have been here since the early solar system, delivered by comets and asteroids to the newly formed Earth, gathered into oceans over hundreds of millions of years. Some of the water falling as rain tonight has been cycling continuously since before there were animals to drink it, since before there were plants to absorb it, since before the first single-celled organisms floated in a warm, shallow sea, learning slowly and blindly to capture energy from light. The water is older than everything that drinks it. This is the water cycle, not a recent invention, not a convenience of modern Earth, but the fundamental operating system of the planet's surface, the mechanism by which water is continuously moved, purified, redistributed, and returned. It has been running in essentially its current form for at least 3.5 billion years, and possibly 4 billion, since enough land had risen above the early ocean for a freshwater cycle to operate. Its steps are the same steps they have always been, and they are worth tracing slowly tonight, one by one, like following a path you have walked 1,000 times in the dark. It begins with the ocean. The ocean covers 70% of the planet's surface and holds about 97% of all the water on Earth. It is the reservoir, the source, the place everything eventually returns to from its surface, warmed by the sun. Water molecules are constantly escaping into the atmosphere, evaporating, turning from liquid to invisible vapor, rising on warm air into the atmosphere above. Evaporation provides nearly 90% of the moisture in the atmosphere. The rest comes from transpiration. the release of water vapor from the leaves of plants and trees, which draw water up from the soil through their roots and breathe it out through tiny pores in their leaves. The Amazon rainforest, as we noted in an earlier section, is so vast and transpires so much water that it generates its own rain. But even a single tree in a garden on an ordinary summer day is contributing molecule by molecule to the moisture in the air above it. The water vapor rises. As it rises, it cools. At the dew point, the temperature at which the air is saturated and can hold no more moisture, condensation begins. Water vapor converts back to liquid water around the microscopic condensation nuclei, dust, sea salt, pollen that float in the atmosphere in their billions. Droplets form. Droplets aggregate. Clouds appear. Inside the cloud, the droplets grow. Through collision and coalescence in warm clouds, through the burgeoning process in cold ones, the same processes we explored in the earliest sections of tonight's journey. The droplets grow until they are too heavy to remain suspended. They fall rain, snow, sleet, hail. The water returns to the surface, and when it arrives, it has choices. Some of it falls back directly onto the ocean, that 90% we mentioned, the rain that falls on water and simply joins it, its journey complete before it has properly begun. Some falls on land, and for this portion, the 10% or so of global precipitation that falls on the continental surfaces, the choices multiply. Some of it runs off the surface immediately, following the contours of the land downhill into streams and rivers, flowing back to the sea in hours or days or weeks. Some is intercepted by vegetation, caught on leaves, absorbed by bark, evaporated before it ever reaches the ground, returned directly to the atmosphere to begin the cycle again. Some soaks into the soil, where it is held in the spaces between soil particles, available to plant roots, available to be drawn up and transpired again. And some of it percolates deeper, passing through the soil, through rock layers, moving slowly downward under gravity until it reaches a zone of saturation in the rock below the groundwater. aquifer, a vast, slow-moving reservoir of water held in the pores and fractures of rock, sometimes meters below the surface, sometimes hundreds of meters down. Groundwater moves slowly, far more slowly than a river. A water molecule that infiltrates into a deep aquifer may take decades or centuries or thousands of years to work its way through the rock and emerge again as a spring, or seep into the bed of a river, or be pumped to the surface by a well. The great aquifers of the world, the Ogallala Aquifer beneath the American Great Plains, the vast aquifer systems beneath the Sahara, the deep aquifers of northern India, contain water that fell as rain during the last ice age and before, water that has been underground for 10,000 years or more. It is still water, still H2O, still the same molecules, waiting in the dark beneath the rock, as they have waited since the glaciers that last recharged them retreated from the landscape. Old rain, ancient rain, locked in stone, the water cycle is not a simple circle. It is a network of loops within loops, operating at different speeds and different scales simultaneously. The surface loop, evaporation, condensation, rain, runoff, cycles water through the atmosphere in days to weeks. The soil moisture loop cycles it through plants and back to the atmosphere in days to months. The river loop delivers it to the ocean in days to years. The groundwater loop may hold it for thousands of years before returning it. The polar ice loop, water locked in glaciers and ice sheets, may hold it for millions of years. All of these loops are running at once. All of them are connected. Water moves from loop to loop, spending some time in each, eventually returning to the ocean to begin the whole journey again. And through all of it, through every evaporation and condensation and rainfall and infiltration and transpiration, the total amount of water on Earth stays essentially constant. No water is created in the water cycle. No water is destroyed. It is simply moved, reorganized, redistributed, purified in the atmosphere, concentrated in the oceans, locked in ice, freed by warmth, carried by rivers, transpired by forests, rained on deserts and mountains and cities, and quiet gardens at midnight, the same water, always the same water, older than the sun, older than the earth it runs across, older than anything that has ever lived in it or depended on it. There is a thought experiment worth holding for a moment. The water molecules in a single raindrop tonight have a history that would fill volumes. Some of those molecules evaporated from the Pacific Ocean last week. Some transpired from a Siberian pine forest 3 months ago. Some fell as snow on a mountain in Norway last winter and melted into a river in spring. Some were locked in Antarctic ice for 100,000 years and released by the warming of recent decades. Some were drunk by an elephant on the African savanna, metabolized and exhaled as breath. Some passed through the roots of wheat in the fields of Ukraine, flowed through the xylem vessels of the stalk, and transpired from the leaf on a warm afternoon, all of them converging into a cloud somewhere over the Atlantic, condensing onto a particle of sea salt or a grain of Saharan dust, coalescing into a drop, falling. One raindrop. All those histories inside it, all those journeys completed, and the next one beginning, right now, wherever it lands. The rain is always in the middle of something, always between where it has been and where it is going. It never stops. It never truly arrives and stays. It passes through the ocean, through the air, through the soil, through the tree, through the river, through the body that drinks it, and continues, as it has always continued, as it will always continue, and you, falling slowly into sleep right now, are part of the same continuous movement. Water in your blood, cycling. Breath leaving your body as vapor, returning. Everything moving gently in the old loop. Humans have been making art about rain for as long as they have been making art. Before writing, before cities, before the wheel or the loom or the fired clay pot. On the walls of caves and the surfaces of rock, in the oldest visual languages we have found, there are depictions of water falling from the sky, not because the artists were trying to document the weather, because rain meant something, because rain was one of the forces that shaped every day of their lives, that determined whether the plants grew or didn't, whether the rivers ran or thinned, whether the year would be generous or hard. And the things that shape our lives tend to find their way into the things we make. Rain is still finding its way into everything we make. There is a painting that hangs in the Art Institute of Chicago that has been called one of the greatest paintings of the 19th century. It was made in 1877 by a French painter named Gustave Caillebotte, and it is simply called Paris Street, Rainy Day. It is a large canvas, more than 2 meters wide, showing a corner in the newly rebuilt Paris of Baron Haussmann, where wide new boulevards replaced the old cramped medieval streets that Napoleon III had decided were inconvenient and unmodern. The day is gray. The cobblestones are wet and reflective. Figures in bourgeois dress move across the intersection, most of them carrying umbrellas. 2 people, a man and a woman, presumably a couple, walk toward the viewer in the center of the frame, their faces composed and private, each one somehow alone in their thoughts, despite their closeness. The rain in Caillebotte's painting is not visible as rain. There are no streaks, no drops, no puddles splashing. But it is everywhere in the gleam of the wet stone, in the gray light, in the forest of black umbrellas, in the particular quality of self-containment that people adopt when they are walking in rain. You know it is raining in this painting without needing to be shown a single drop. The rain is in the atmosphere of it. This is what artists discovered about rain, that its most interesting qualities are not the drops themselves, but what the drops do to everything else, to the light, to the color of surfaces, to the behavior of the people caught in it. The Japanese printmakers of the ukiyo-e tradition understood this perfectly. Utagawa Hiroshi, sometimes called the poet of rain, made rain one of the defining subjects of his long career. His prints show rain as diagonal lines, dozens of them, drawn across a scene with a calligrapher's brush, overlaying the landscape beneath with a curtain of falling water that suggests both the visual appearance and the force and movement of rain in a way that Western painting of the same period rarely achieved. Vincent van Gogh was so struck by Hirschheimer's treatment of rain that he made a direct copy of one of his prints in oil paint, studying it as a student studies a master, learning how to make falling water visible with lines. That painting, Bridge in the Rain, hangs today in the Van Gogh Museum in Amsterdam. And the thin, dark, vertical strokes Van Gogh used to render the rain are directly descended from Hirschheimer's calligraphic brushwork, an inheritance passed from a Japanese printmaker to a Dutch painter through the medium of rain. But rain in visual art is not always melancholy. In Japanese artistic tradition, rain carries meanings quite different from its associations in Western art, where a British painter might use rain as a metaphor for gloom or grief, or the oppressive weight of circumstance. Japanese artists treated rain as a necessity, a blessing, something to be grateful for. The sight of rain in a Japanese woodblock print often signals abundance, fertility, the continuation of the natural order. Rain is not interrupting life. It is enabling it. Indian miniature painting had its own rich tradition of rain imagery, centered on the monsoon. The tradition of Ragamala painting, paintings made to accompany and visualize specific musical ragas, included an entire family of ragas associated with the monsoon. The raga Megmalhar, directly associated with rain, and the monsoon season was painted with dark, billowing clouds, peacocks dancing. For the peacock is considered in India a herald of monsoon rain, and the figures of Krishna and Radha, the divine lovers whose relationship is traditionally celebrated in the rainy season, the monsoon as romance, rain as the setting for the meeting of lovers. In the Indian aesthetic tradition, the mood of the monsoon, the charged, anticipatory atmosphere of the approaching rains, the relief and joy of their arrival, was inseparable from the emotional quality of longing and reunion. Rain opened something in the landscape, and the artists of the Rajput schools captured that opening, that release, in paintings of extraordinary color and tenderness. Rain in literature is equally pervasive and equally varied in its meanings. The writers of the English Romantic tradition, Keats, Shelley, Byron, Wordsworth, were drawn to rain as an external correlative of the interior emotional life. Rain falling on a landscape could express grief, longing, the weight of mortality, the sublime indifference of nature to human suffering, the curve of a rainstorm across a moorland, the drip of water from an eave, the sound of rain on a tin roof in the night. These were not just settings for the emotional life, but extensions of it, the weather inside and the weather outside corresponding. In the 20th century, rain in literature became something more ambiguous and more modern. Ernest Hemingway famously used rain throughout A Farewell to Arms as an omen of disaster. Characters die in the rain. Bad things happen in the rain. And he used it with such deliberate restraint that it becomes one of the most quietly powerful motifs in American fiction, not melodrama. Just rain at the wrong moments and the particular feeling that gives. Film discovered rain almost immediately. The sound of rain on a window, rain on a pavement, rain falling on a night scene photographed in black and white. These became some of the most enduring images of cinema. Think of Gene Kelly's Singin' in the Rain, the famous solo dance sequence in which he abandons his umbrella and moves through a torrential downpour with a freedom and joy that the dry weather world apparently couldn't contain. The rain in that scene is not interrupting his happiness. It is the only adequate expression of it. Music, too, has returned to rain again and again across every tradition and every century, from the monsoon ragas of classical Indian music, composed to evoke the specific emotional quality of rain on a particular night in a particular season, to the piano piece La Pluie by Chopin, in which the right hand's repeating note pattern suggests the steady tap of drops on a surface, to the countless popular songs that have used rain as a vehicle for love, grief, nostalgia, and the complicated feeling of being inside and warm, while the world outside is wet and dark. Rain songs are their own genre, really. They share something, a particular quality of enclosure, of interiority, of the emotional permission that rain grants. The world outside is wet and busy. In here, there is a pause. In here, something can be felt that the ordinary dry world moves too fast to accommodate. That is what rain has always given art. Not just subject matter, but atmosphere. Not just a thing to paint or write or compose, but a particular quality of time and feeling. Slower, more interior, more open to what is usually submerged beneath the noise of ordinary days. Art about rain tends to be quiet, even when it is joyful, even when it is Gene Kelly jumping into puddles. It is interior joy, private joy, the joy of a person who has, for a moment, found the weather outside matching something they were already feeling inside, and that, perhaps, is what all the rain art across all the centuries and all the cultures is really about. Not the water itself, not the meteorology, not the drops and the clouds and the barometric pressure, but the recognition, the sudden, startling, unexpectedly moving recognition that the sky is feeling something too, that the weather outside is, for a moment, the same as the weather within. You are not alone in this. The sky has been keeping you company. It always has. For most of human history, nobody slept the way we sleep now. The idea of a single, continuous 8-hour block of sleep, the modern ideal, the thing we are told we need, and told we are failing to get, is, in the long story of our species, a very recent invention. It arrived with the electric light bulb and the factory shift and the standardized workday. And it replaced something much older and much stranger, and in its own way, much more in harmony with the rhythms of the natural world. What it replaced was called segmented sleep, or biphasic sleep. 2 sleeps in the language of the historical record. And rain and darkness and the long nights of seasons before electric light had anything to do with how it worked. Here is how a night looked for most people in pre-industrial Europe. across much of the pre-industrial world for thousands of years. The sun went down. Candles and firelight were expensive, and ordinary households did not burn them for long after dark. The work of the day was finished, and so, reasonably early in the evening, perhaps 8 or 9 o'clock, people went to bed, not to read, not to scroll through anything, simply to sleep. They slept for approximately 4 hours, and then they woke up. This waking, around midnight or 1 in the morning, was not insomnia. It was not a malfunction. It was entirely expected, entirely normal, and entirely accounted for in the structure of the night. References to this waking, called variously the first sleep, the dead sleep, or simply the first rest, appear in historical documents across many centuries and many cultures. They appear in Chaucer, they appear in Homer's Odyssey and Virgil's Aeneid. They appear in English court records, in French legal documents, in medical texts advising on the best time to take medicines or conceive children. They appear in letters and diaries and parish registers in a dozen languages. And the historian Roger Eckhart, who spent decades tracking down these references, eventually found more than 2,000 of them, stretching from ancient Greece to the early 19th century. 2,000 references to the first sleep, to the assumption that waking in the middle of the night was a normal and expected thing. What did people do during the hour or 2 between their first sleep and their second? The records suggest a remarkable variety of quiet, intimate, middle-of-the-night activities. They prayed. Many people kept a book of hours beside the bed and used the waking interval for devotional reading or contemplation. The quiet middle-of-the-night hours were considered particularly conducive to spiritual reflection. The mind softened by sleep and not yet hardened by the demands of day. They talked. Couples talked in the darkness. Families with children talked. The hour between the sleeps was a social time, private and warm, without the structure or obligation of daylight hours. They also, apparently, remembered their dreams with unusual clarity in this waking interval. The dreams of the first sleep still vivid and available in a way that morning dreams rarely are. And in some households, the period between sleeps was a time for discussing what the dreams might mean, not in any formal or superstitious way necessarily, simply in the way that people have always shared the strange interior landscapes of sleep with whoever was beside them in the dark. Some people got up. Briefly, they checked the fire, or the animals, or the children. They ate something light, or drank some water, or used the chamber pot, and then returned to bed for the second sleep. The longer, deeper, more continuous sleep that lasted until dawn. This was the whole night. 2 sleeps with a quiet waking between them. And through all of it, through the first sleep and the waking interval and the second sleep, the weather outside continued its business in the long, cold winters of northern Europe. Snow fell silently on the thatch and stone of the villages. In autumn, rain fell steadily on the fields that had just been harvested. In spring, it rained again, and the sound of it on the shuttered windows was part of the soundscape of the night, as familiar and unremarkable as the creak of the house settling in the cold rain on a night with no electric light, no traffic, no ambient noise of any kind, is a very different experience from rain as we know it now. In genuine pre-industrial darkness and silence, the sound of rain fills the acoustic world almost completely. There is nothing competing with it. The drip from a thatch roof, the movement of water in a ditch or a lane outside, the particular hiss of rain on a vegetable garden or an orchard, each leaf contributing its note. People slept inside all of that. They woke inside it in the middle of the night, in their small, warm beds, surrounded by the cold and the dark and the rain. And they spoke quietly to each other, or lay still and listened to the rain. And then they slept again. Researchers studying sleep in pre-industrial communities that still exist today. Small groups in Bolivia, Tanzania, and Namibia, living without electricity and following patterns that may resemble those of our evolutionary ancestors, have found something interesting These communities do not sleep longer than modern people. They sleep roughly similar amounts, but their sleep is organized differently, shaped by temperature rather than by light. They tend to fall asleep when the environmental temperature begins to drop in the evening, and wake naturally as it rises again around dawn. Temperature and darkness, not alarm clocks and screens, the body following the signals the planet provides. And the planet's signals for most of the year in most of the temperate world include rain. Rain dropping the temperature. Rain darkening an already dark sky. Rain filling the soundscape with pink noise that covers the acoustic gaps through which wakefulness might otherwise creep back in. Rain saying, reliably and without fail, the same thing it has always said to a body lying in a dry and sheltered place. There is nothing to do out there tonight. Come back to sleep. The Industrial Revolution changed all of this, and changed it relatively quickly. The factory system required standardized work shifts, large groups of workers arriving and leaving at the same time, and standardized labor meant standardized sleep. You could not sleep in 2 segments if you had to be at the mill by 6 in the morning. The single consolidated sleep became necessary, not because it was natural, but because the economy required it, and as gas lighting, and then electric lighting, pushed the end of the day later and later, the beginning of the first sleep shifted later too, compressing the whole night and eliminating the quiet waking interval that had once been part of every ordinary night. The historian A. Roger Eckhart argues that this compression of sleep may be one of the underappreciated sources of the modern epidemic of middle-of-the-night wakefulness, when people wake at 2 or 3 in the morning in a state of anxiety. The particular pressurized wakefulness of a sleepless night that feels wrong and alarming and in need of fixing. They may partly be experiencing a very ancient biological rhythm asserting itself against the modern expectation of unbroken sleep. The body, perhaps, is still reaching for the quiet waking interval that it was shaped by evolution and history to expect. It waits check. No partner ready to talk quietly in the dark. No prayer book beside the bed. It finds instead a phone, a to-do list, the ambient anxiety of a connected world. And what was once a restful pause in the middle of the night becomes something that feels like failure. Knowing this history does not fix insomnia, but it changes its meaning slightly. If you wake tonight in the small hours and find yourself not quite asleep, not quite anxious, simply present in the darkness, you are doing something your ancestors did every night without distress. You are in the space between the first sleep and the second, the quiet interval, the hour that was once filled with the sound of rain on old rooftops and the low voices of people telling each other what they had dreamed. You are not failing to sleep. You are in the oldest part of the night, the part that predates alarm clocks and factories and the electric light and the single consolidated A-tower block that we have told ourselves is the only acceptable way to be unconscious. The rain outside, if there is rain, is the same rain that fell on those pre-industrial rooftops, on the thatch and the stone, on the vegetable gardens, on the lanes and the fields, on all the sleeping and the quietly waking people lying in their warm beds in the long dark of a winter night, talking softly to each other, or simply listening to the sound of the water finding its way down through the night to wherever it was going. That hour belongs to you. If sleep comes, let it come. If it does not come immediately, let the rain fill the space until it does. You are exactly where you are supposed to be, in the oldest part of the night, waiting for the second sleep. For most of human history, nobody slept the way we sleep now. The idea of a single, continuous 8-hour block of sleep, the modern ideal, the thing we are told we need, and told we are failing to get, is, in the long story of our species, a very recent invention. It arrived with the electric light bulb and the factory shift and the standardized workday. And it replaced something much older and much stranger, and in its own way, much more in harmony with the rhythms of the natural world. What it replaced was called segmented sleep, or biphasic sleep, two sleeps in the language of the historical record, and rain and darkness, and the long nights of seasons before electric light had anything to do with how it worked. Here is how a night looked for most people in pre-industrial Europe and across much of the pre-industrial world for thousands of years. The sun went down. Candles and firelight were expensive, and ordinary households did not burn them for long after dark. The work of the day was finished, and so, reasonably early in the evening, perhaps 8 or 9 o'clock, people went to bed, not to read, not to scroll through anything, simply to sleep. They slept for approximately 4 hours, and then they woke up. This waking around midnight or 1 in the morning was not insomnia. It was not a malfunction. It was entirely expected, entirely normal, and entirely accounted for in the structure of the night. References to this waking, called variously the first sleep, the dead sleep, or simply the first rest, appear in historical documents across many centuries and many cultures. They appear in Chaucer, they appear in Homer's Odyssey and Virgil's Aeneid. They appear in English court records, in French legal documents, in medical texts advising on the best time to take medicines or conceive children. They appear in letters and diaries and parish registers in a dozen languages. And the historian Roger Eckhart, who spent decades tracking down these references, eventually found more than 2,000 of them, stretching from ancient Greece to the early 19th century. 2,000 references to the first sleep, to the assumption that waking in the middle of the night was a normal and expected thing. What did people do during the hour or two between their first sleep and their second? The records suggest a remarkable variety of quiet, intimate, middle-of-the-night activities. They prayed. Many people kept a book of hours beside the bed and used the waking interval for devotional reading or contemplation. The quiet middle-of-the-night hours were considered particularly conducive to spiritual reflection. The mind softened by sleep and not yet hardened by the demands of day. They talked. Couples talked in the darkness. Families with children talked. The hour between the sleeps was a social time, private and warm, without the structure or obligation of daylight hours. They also, apparently, remembered their dreams with unusual clarity in this waking interval. The dreams of the first sleep still vivid and available in a way that morning dreams rarely are. And in some households, the period between sleeps was a time for discussing what the dreams might mean, not in any formal or superstitious way necessarily, simply in the way that people have always shared the strange interior landscapes of sleep with whoever was beside them in the dark. Some people got up. Briefly, they checked the fire or the animals or the children. They ate something light or drank some water or used the chamber pot, and then returned to bed for the second sleep. The longer, deeper, more continuous sleep that lasted until dawn. This was the whole night. 2 sleeps with a quiet waking between them. And through all of it, through the first sleep and the waking interval and the second sleep, the weather outside continued its business in the long, cold winters of northern Europe. Snow fell silently on the thatch and stone of the villages. In autumn, rain fell steadily on the fields that had just been harvested. In spring, it rained again, and the sound of it on the shuttered windows was part of the soundscape of the night, as familiar and unremarkable as the creak of the house settling in the cold rain on a night with no electric light, no traffic, no ambient noise of any kind, is a very different experience from rain as we know it now. In genuine pre-industrial darkness and silence, the sound of rain fills the acoustic world almost completely. There is nothing competing with it. The drip from a thatch roof, the movement of water in a ditch or a lane outside, the particular hiss of rain on a vegetable garden or an orchard, each leaf contributing its note. People slept inside all of that. They woke inside it in the middle of the night, in their small, warm beds, surrounded by the cold and the dark and the rain. And they spoke quietly to each other, or lay still and listened to the rain. And then they slept again. Researchers studying sleep in pre-industrial communities that still exist today. Small groups in Bolivia, Tanzania, and Namibia, living without electricity and following patterns that may resemble those of our evolutionary ancestors, have found something interesting. These communities do not sleep longer than modern people. They sleep roughly similar amounts, but their sleep is organized differently, shaped by temperature rather than by light. They tend to fall asleep when the environmental temperature begins to drop in the evening, and wake naturally as it rises again around dawn. Temperature and darkness, not alarm clocks and screens, the body following the signals the planet provides. And the planet's signals for most of the year in most of the temperate world include rain. Rain dropping the temperature. Rain darkening an already dark sky. Rain filling the soundscape with pink noise that covers the acoustic gaps through which wakefulness might otherwise creep back in. Rain saying, reliably and without fail, the same thing it has always said to a body lying in a dry and sheltered place. There is nothing to do out there tonight. Come back to sleep. The Industrial Revolution changed all of this, and changed it relatively quickly. The factory system required standardized work shifts, large groups of workers arriving and leaving at the same time, and standardized labor meant standardized sleep. You could not sleep in 2 segments if you had to be at the mill by 6 in the morning. The single consolidated sleep became necessary, not because it was natural, but because the economy required it, and as gas lighting, and then electric lighting, pushed the end of the day later and later. The beginning of the first sleep shifted later too, compressing the whole night and eliminating the quiet waking interval that had once been part of every ordinary night. The historian A. Roger Eckhart argues that this compression of sleep may be one of the underappreciated sources of the modern epidemic of middle-of-the-night wakefulness, when people wake at 2 or 3 in the morning in a state of anxiety. The particular pressurized wakefulness of a sleepless night that feels wrong and alarming and in need of fixing. They may partly be experiencing a very ancient biological rhythm, asserting itself against the modern expectation of unbroken sleep. The body, perhaps, is still reaching for the quiet waking interval that it was shaped by evolution and history to expect. It wakes and finds no fire to check, no partner ready to talk quietly in the dark, no prayer book beside the bed. It finds instead a phone, a to-do list, the ambient anxiety of a connected world. And what was once a restful pause in the middle of the night becomes something that feels like failure. Knowing this history does not fix insomnia, but it changes its meaning slightly. If you wake tonight in the small hours and find yourself not quite asleep, not quite anxious, simply present in the darkness, you are doing something your ancestors did every night without distress. You are in the space between the first sleep and the second, the quiet interval, the hour that was once filled with the sound of rain on old rooftops and the low voices of people telling each other what they had dreamed. You are not failing to sleep. You are in the oldest part of the night, the part that predates alarm clocks and factories and the electric light and the single consolidated A-tower block that we have told ourselves is the only acceptable way to be unconscious. The rain outside, if there is rain, is the same rain that fell on those pre-industrial rooftops, on the thatch and the stone, on the vegetable gardens, on the lanes and the fields, on all the sleeping and the quietly waking people lying in their warm beds in the long dark of a winter night, talking softly to each other, or simply listening to the sound of the water finding its way down through the night to wherever it was going. That hour belongs to you. If sleep comes, let it come. If it does not come immediately, let the rain fill the space until it does. You are exactly where you are supposed to be, in the oldest part of the night, waiting for the second sleep. Most rain moves quickly. It falls and runs off and finds a stream, and the stream finds a river, and the river finds the sea, and the whole transaction is completed in days or weeks. The rain is received and dispatched. It passes through the land, the way a traveler passes through a town, briefly, purposefully, on its way to somewhere else. But in some places, the rain stays. It finds low ground that drains slowly, or no ground at all beneath the water table, or a layer of clay that resists infiltration, or a cold and boggy hollow where evaporation is slow and rainfall generous. It settles, it pools, it soaks into deep beds of moss and peat. It turns the land into something between solid and liquid, not dry enough to walk on comfortably, not wet enough to swim in. Something in between, a wetland. Wetlands are the places where rain lingers, where the water cycle slows to something close to stillness, taking its time in a way that rivers and streams do not. And in that slowing, in that patient accumulation of water in low, still, waterlogged places, something extraordinary happens. Life finding conditions that exist nowhere else, builds some of the most complex and productive ecosystems on the surface of the earth. There are 4 main kinds of wetland, each with its own character and its own relationship to rain. The marsh is perhaps the most familiar. A marsh is a wetland of open water and emergent vegetation. Cattails and bulrushes and reeds standing knee-deep or waist-deep in slow, still, or very gently flowing water, their roots below the water line and their stems rising into the air. Freshwater marshes form at the edges of lakes and along slow rivers in the places where the land is too low and too wet to be dry ground, but too shallow to be open water. They are intensely alive. The shallow, warm, nutrient-rich water of a freshwater marsh is a nursery and a larder and a shelter simultaneously. Fish spawn in the dense stems of aquatic plants. Frogs lay their eggs in the still margins. Herons stand motionless in the shallows for long minutes, then strike with a speed that seems impossible for something so patient. Migratory birds arrive in their millions in spring and autumn, using the marshes as refueling stations on journeys of thousands of miles. Dragonflies hover over the surface, iridescent in the slanted light of an afternoon, hunting insects with a precision and efficiency that has been essentially unchanged for 300 million years. The The swamp is a marsh's older, darker sibling, where marshes are open and grassy. Swamps are treed. The bald cypress swamps of the American South, those cathedral spaces of gray water and hanging moss, and the strange, knobbly root structures called cypress knees rising from the flood, are swamps, water-tolerant trees standing in shallow water, their canopies closing above into a dim, humid, green-filtered light. Tupelo and willow and red maple in cooler northern swamps, mangroves in tropical coastal swamps, their tangled prop roots creating labyrinths of still water and mud that serve as nurseries for an astonishing proportion of the world's tropical fish species to paddle a canoe into a cypress swamp on a still morning is to enter a world that seems to belong to a different age. The water is dark, stained brown by tannins leaching from the fallen leaves, the color of strong tea, and perfectly smooth, and the reflections of the trees in it are so clear and so still that the boundary between real and reflected is difficult to locate. There is no wind. There is bird song and the occasional splash of something unseen and the soft drip of water from a paddle blade, and that is all. Then there are the bogs and the fens, which are the wetlands most completely defined by rain. A bog is, in essence, a wetland that drinks only rain. No stream feeds it. No groundwater rises into it from below. A bog receives its water entirely from precipitation. Rain and snow falling directly on its surface, and it loses water only through evaporation and the slow seepage of water at its margins. Everything that is in a bog arrived from the sky. This dependence on rainfall alone gives bogs their distinctive and extreme chemistry. Rainwater is naturally slightly acidic. It absorbs carbon dioxide from the atmosphere as it falls, forming a weak carbonic acid in a bog with no groundwater or stream water to neutralize this acidity. The water becomes dramatically acidic over time, often reaching pH levels of 3 to 4, more acidic than vinegar. Almost nothing can live in such conditions. Almost nothing, but not quite nothing. The dominant plant of the bog, the plant that makes the bog, that builds it and sustains it and shapes everything else about it, is sphagnum moss. Sphagnum is one of the most remarkable plants on earth. It is not fussy about nutrients, since there are almost none available. It tolerates, and in fact produces, the extreme acidity of the bog water. It grows continuously from its tips, while its lower portions die. And those dead lower portions do not decompose. The acidic, low oxygen conditions of the bog water prevent the bacteria and fungi that would normally break down dead plant matter from doing their work. Instead, the dead sphagnum accumulates, layer on layer, century on century, millennium on millennium, compressed by its own weight into the dense, dark, fibrous material called peat. A deep peat bog may have been accumulating for 10,000 years. Its deepest layers were growing, while the last ice age was still ending, and the first human farmers were just beginning to plant their first fields. Every millimeter of peat is a year of moss, slowly compressed, slowly preserved in the cold acid dark. Peat bogs are, in consequence, extraordinary archives. The acid anaerobic conditions that preserve the sphagnum also preserve almost everything else that falls into a bog. Pollen from ancient forests, laid down year by year, tells paleobotanists what plants were growing in the landscape around the bog for thousands of years. Beetles and insects, perfectly preserved, tell entomologists what species lived in the area in each period. Tree trunks fallen into bogs thousands of years ago emerge still intact when bogs are cut for fuel. The wood darkened to near black by the tannins, but structurally sound. And most remarkably, people, the bog bodies, dozens of them, found across northern Europe over the centuries, preserved by the same chemistry that preserves everything else in a bog. Iron Age men and women, some of them hundreds or thousands of years old, their skin tanned dark, their hair still present, their last meals sometimes still identifiable in their stomachs, found in Danish bogs, in Irish bogs, in German bogs, lying in the peat with the quiet composed stillness of people who have been asleep for a very long time. A bog is patient with what it receives. It keeps things. The fen is the bog's more sociable neighbor. Where a bog receives only rain, a fen receives water from groundwater and from streams draining off surrounding mineral soils as well. This additional water is richer in dissolved minerals, calcium, magnesium, the nutrients that the bog's reliance on rain alone cannot provide. The fen is less acidic, more fertile, and supports a much greater diversity of plants. Sedges and rushes and wildflowers grow alongside the mosses. The water is clearer and the vegetation more varied, and the whole community more diverse and more welcoming than the stark, specialized world of a bog. But perhaps the most important thing about wetlands, all of them, marsh and swamp and bog and fen, is what they do with rain that no other landscape does quite as well. They slow it down when rain falls on a wetland. It does not run off immediately. It is absorbed into the moss and the saturated soil and held there, released gradually, seeping slowly out at the margins over days and weeks. A wetland acts as a sponge for the watershed around it. In periods of heavy rain, the wetland fills and absorbs the excess, preventing floodwaters from overwhelming the rivers and streams downstream. In dry periods, the wetland releases its stored water slowly, keeping the streams fed long after the rain has stopped. This function, flood control, and dry season water storage, is worth enormous amounts of money in engineering terms. Wetlands provide this service for free, powered only by rain and gravity and the patient growth of sphagnum and sedge. And then there is what wetlands do with carbon. Peat bogs and other wetlands store more carbon per hectare than almost any other ecosystem on Earth. Up to 40 times more carbon than forests, stored in the deep organic soils that accumulate over centuries. The world's peatlands, most of them in northern latitudes, in Canada and Russia and Scandinavia and Ireland, store approximately a third of all the carbon in the world's soils, despite covering only 3% of the land surface, all of it built from rain and moss, layer by layer, in the slow, cold, acid dark. Carbon captured from ancient atmospheres and held underground patiently for thousands of years. Rain arriving, being received, being kept. There is something in the quality of a wetland, in the stillness of its water and the softness of its ground, and the particular muffled quiet of a place where the land is neither solid nor liquid, where the ordinary rules of landscape are suspended. That is unlike any other environment. You can sit beside a bog on a gray morning and hear almost nothing except the occasional call of a curlew somewhere in the reeds and the faint movement of wind across the sedge, and feel a stillness that is not emptiness but fullness, a place that is quietly, completely, deeply itself, doing exactly what it has been doing for 10,000 years, receiving rain, keeping things, building its patient dark layers, one thin, slow millimeter at a time. The rain that falls on a bog tonight will still be there in the morning. It will still be there in some form for a very long time. Let that patience be yours tonight. Still, receiving, keeping the quiet. Rain changes the color of everything. This is one of those observations so obvious that it rarely gets examined. And yet, when you stay with it long enough, it opens into something genuinely beautiful. The world before rain, and the world during rain, and the world after rain are, in a very real optical sense, three different worlds. The same streets, the same trees, the same hills and rooftops and garden walls, but in different light, with different surfaces, under a different quality of sky. And so, to the eye and the brain, in different colors entirely, before we can understand what rain does to color, we need to spend a moment with light itself. Sunlight appears white. Or rather, it appears to have no color. It is the default, the baseline, the thing we see when we are not noticing color at all. But white light is not simple. It is a mixture, a blend of every color in the visible spectrum. Every wavelength from the deep red end to the violet end, combined in proportions that our visual system reads as colorless. When that mixed light hits a surface, the surface absorbs some wavelengths and reflects others. The wavelengths it reflects are the ones our eyes detect, and that combination is what we experience as the color of the object. A red apple is not intrinsically red. It is an object that absorbs most of the spectrum and reflects the red wavelengths back toward our eyes. A green leaf reflects the green wavelengths. A gray wall reflects all wavelengths roughly equally, but weakly, giving the impression of a neutral, low-intensity version of the full spectrum. And when the sky is overcast, when thick cloud cover replaces the direct sun with a diffuse, scattered, even illumination from all directions at once, the color of everything beneath it shifts, shadows disappear. The harsh contrast between light surfaces and dark ones softens. The world becomes more evenly lit from above and from the sides, and in that even lighting, colors that were bleached out by direct sunlight or lost in harsh shadow become visible. Painters have known this for centuries. The light on a cloudy day before rain is, in many ways, better light for seeing color than bright sunlight. It is the light of a north-facing studio window, consistent, soft, revealing the green of wet grass under gray cloud, is a richer, deeper, more saturated green than the same grass under high summer sun. The colors of a flower bed before a rain are gentler and more complete than they are under direct light. The world, paradoxically, is in some ways more colorful in the gray light of an approaching storm than it is in full sun. And then the rain actually falls, and another transformation happens. Rain wets surfaces, and wet surfaces behave differently with light than dry surfaces do. A dry stone wall has a rough, matte surface. Light striking it scatters in every direction. This is called diffuse reflection, and the result is the pale, muted tone of dry stone. But when rain wets the wall, the water fills the small irregularities in the surface, smoothing it at the microscopic level, and the surface becomes partly specular. It partially reflects light in a more directed way, like a mirror. The color of wet stone is deeper, richer, more saturated than dry stone, because the water film is absorbing some light and allowing the surface's own color. The iron oxides and mineral tones locked in the rock to express itself more fully. This is why everything looks more vivid immediately after rain. Wet bark, wet leaves, wet brick, wet pavement, all of them richer and darker and more saturated than their dry versions. A garden after rain is visually more intense than the same garden on a dry day. The greens more green, the reds more red, the gray of the old stone wall more deeply and beautifully gray. Rain is, in a sense, a color enhancer. It brings the world's surfaces closer to what they actually are. And then there is what happens to light inside a single raindrop. A raindrop falling is a near-perfect sphere of water, one of the most optically interesting shapes in nature. When sunlight enters a raindrop, it slows down. Light travels more slowly in water than in air, and as it crosses from one medium to another at an angle, it bends. This bending is called refraction, but crucially, different wavelengths of light bend by different amounts. Red light bends slightly less than orange light, which bends slightly less than yellow light, and so on across the spectrum, down to violet, which bends the most. White light enters the raindrop as a single mixed beam and exits as a fan, each color separated from the others by its slightly different angle of refraction. The whole spectrum spread out in the precise sequence that we call the rainbow. The result is that light exits the raindrop at a very specific angle, about 42 degrees from the direction of the incoming sunlight for red light, and about 40 degrees for violet. And each wavelength exits at its own specific angle. The colors sorted into their positions in the spectrum, what we call a rainbow, is millions of raindrops, each one doing this simultaneously, each one sending its small separated spectrum toward the observer at its own precise angle. And the observer's eye assembling all these small contributions into the great arc of color that appears to hang in the sky opposite the sun. The rainbow is not a thing. It is a view. It is the particular result of being in a particular position relative to the sun and the rain, with your eye at the exact angle where each color from each drop aligns with your line of sight, moves sideways, and the rainbow moves with you. Always the same angular distance from the point directly opposite the sun, because the geometry is fixed. This is why you can never reach the end of a rainbow. The end is always the same angular distance away from you. As you walk toward it, it retreats by exactly the amount you advance. There are rainbows within rainbows. The secondary rainbow, visible as a larger, fainter arc above the primary bow, with its colors in the reverse order, forms from light that has reflected twice inside each raindrop before exiting. The extra reflection, reversing the sequence of colors between the primary and secondary bows. The sky is noticeably darker than outside them. A band called Alexander's Dark Band, named after the Greek philosopher Alexander of Aphrodisias, who described it in the 3rd century inside the primary bow and outside the secondary. The sky is brighter. The difference is real and measurable and visible on a clear rainbow day, and most people never notice it. And then there are the rarer optical phenomena that rain and near-rain conditions produce. The fog bow, a rainbow formed in fog droplets, which are so small that the colors wash out, and the bow appears almost white. A ghostly, colorless arc floating in gray fog, wider than a true rainbow, and without its brilliance, moonbows, rainbows formed by moonlight, visible only on very bright full moon nights, when rain is falling opposite the moon. Pale and white to the naked eye, human vision loses color sensitivity in low light, but recorded on long exposure photographs as fully colored arcs of light across a dark sky, sun dogs, technically called parhelia. Two bright spots of light appearing on either side of the sun at the same elevation on days when high cirrus clouds are filled with hexagonal ice crystals. The crystals act as tiny prisms, refracting sunlight to specific angles, creating these brilliant patches of colored light, flanking the sun like attendants. Seen from a distance, they can look like two extra suns. They appear most often in cold weather, in the pale winter light of northern latitudes, and they have been remarked upon and recorded since ancient times, mentioned in Roman chronicles, in Norse sagas, in the journals of explorers in the Arctic, and the color of the sky itself during rain. The gray of an overcast sky is not a single gray, but a shifting, variable thing. The particular gray of a thin, high stratus on a bright winter morning, almost white, almost luminous. The sun, a brilliant blurred disk, somewhere behind it, the deep, bruised gray-green of the sky, at the base of a cumulonimbus, before a serious thunderstorm. A color that artists have tried for centuries to capture, and never quite have. The silver gray of a steady frontal rain in late autumn, a gray that contains every other color inside it, compressed and quieted and held in a soft, uniform light that falls on everything equally. Rain changes the sky's palette from the sharp primaries of a clear day, blue above, yellow-white sun, black shadows, to something more complex and more subtle, more tones, more intermediary states. The world under rain is a world of gradients and transitions, not edges, of soft light and soft shadow, and the particular visual texture of a world seen through water. Painters love this. Photographers love this, and somewhere in the human visual system, in the part that has been looking at rainy landscapes since before we had words for any of it, there is a response to the color of rain that is different from the response to any other kind of light, something quieter, something that reads the soft gray light and the deep wet green and the dark reflective wet stone, and assembles them into a single sensation that is not quite named by any single word. The color of rain, the color of being inside while it falls, the color of this particular hour. Let it fill whatever space is behind your closed eyes now, soft and gray and rich and still. When rain falls on bare soil, something you can hear happens first. A single large raindrop strikes the surface with a force entirely disproportionate to its size. Moving at several meters per second, it hits the soil and briefly excavates a tiny crater, throwing particles of soil outward in a miniature splash that can carry those particles several centimeters from the point of impact. Repeat this across an entire field, across an entire hillside, across hours of steady rainfall, and the cumulative energy of all those tiny impacts is extraordinary. A constant, gentle, rhythmic bombardment that gradually reorganizes the surface of the soil, sealing fine particles into the spaces between larger ones, creating what soil scientists call a surface crust. But underneath that surface, something else entirely is happening. Something alive. Something that has been happening in the soil beneath every rain that has ever fallen on land for hundreds of millions of years. Soil is not dirt. This is the first and most important thing to understand about it. Dirt is what you wash off your hands. Soil is an ecosystem, one of the most complex, densely populated, and biologically diverse ecosystems on the surface of the earth, most of it invisible to the naked eye, almost all of it misunderstood, essentially all of it absolutely essential to everything that grows. A single teaspoon of healthy soil contains more individual living organisms than there are people on Earth. Bacteria in numbers beyond meaningful imagining. Fungi threading their microscopic filaments through every available space between soil particles, protozoa grazing on bacteria, nematodes, tiny thread-like roundworms grazing on protozoa, mites, springtails, beetles, and insect larvae, each occupying their specific position in a food web of extraordinary complexity, and threading through all of it, the earthworms. Rain, when it comes, transforms this entire community. In dry periods, soil biology slows. Many bacteria form spores, protective shells that allow them to survive desiccation, waiting in a state of suspended animation for moisture to return. Fungi retract their surface threads and hunker down in their deeper networks. The soil community does not die in a drought. It waits. And when rain comes, the waiting ends with a burst of activity that is one of the most dramatic biological events in the natural world. Even though it happens entirely out of sight and in almost complete silence, water entering dry soil moves through it by capillary action, drawn into the spaces between particles by the attractive force between water molecules and soil surfaces. As it moves, it dissolves the crust of dried organic compounds that accumulated during the dry period, releasing them as soluble nutrients. Bacterial spores detect moisture and germinate within minutes, sometimes within seconds, emerging from their dormancy and beginning to feed and divide at rates that would double the population in hours if conditions were ideal. This explosion of bacterial activity, happening simultaneously throughout the moist soil, releases gases, including the volatile organic compound geosmin, the primary contributor to Petrichor. The smell of rain on dry earth that we explored in an earlier section, the smell you can detect before the rain has properly arrived, is, in part, the smell of dormant soil biology beginning to wake up. The fungi, too, respond rapidly. The mycorrhizal fungi, those that live in intimate association with plant roots, extending the roots' effective reach through vast networks of filaments called hyphae, begin extending new growth within hours of rain arriving after a dry period. These fungal networks are among the most important structures in the living soil. A single plant connected to a mycorrhizal network has effective access to water and nutrients across an area many times larger than its root system alone could cover. The network is not passive. It actively seeks water, detects gradients of soil moisture, and guides the growth of its hyphae toward wetter zones, channeling that water back toward the plant roots it serves. The mycorrhizal network also connects plants to each other. Trees in a forest are linked through shared fungal networks that can transport water, carbon, and chemical signals between individuals. A fact so counterintuitive when first discovered that ecologists who described it were initially met with considerable skepticism, but the evidence is robust. Carbon fixed by photosynthesis in the leaves of a large tree can be transported through the fungal network to a neighboring seedling growing in deep shade, supplementing the seedling's own limited photosynthesis. Rain that enters the soil around the large tree can be redistributed through the network to drier areas where other plants are growing. The forest, in this sense, is not a collection of competing individuals. It is a community with shared infrastructure. And rain is the event that activates that infrastructure most fully, replenishing the moisture that the network uses to function, triggering the growth of new fungal threads into previously dry zones, reconnecting parts of the network that may have retreated or died back during a dry period. And then there are the earthworms. There are roughly 3,000 species of earthworm worldwide, ranging from the common garden earthworm, a few centimeters long, to the giant Gippsland earthworm of Australia, which can reach over a meter in length and makes an audible gurgling sound as it moves through its burrow. What they all share is their method of feeding and their extraordinary effect on soil. An earthworm eats soil. It ingests organic matter, dead leaves, fungi, bacteria, decaying plant roots, mixed with mineral soil particles, passes the mixture through its digestive system, and excretes it as worm casts. Those casts are not simply soil that has been through a worm. They are chemically transformed. Nutrients that were locked in organic matter and unavailable to plant roots are converted in the earthworm's gut into soluble forms that plants can directly absorb. Worm casts are richer in available nitrogen, phosphorus, and potassium than the surrounding soil. Some research suggests they contain 4 times more available phosphorus than the soil from which they came, and the physical effect of earthworms on soil is as significant as the chemical one. As earthworms burrow, they create channels, macropores, running vertically and horizontally through the soil. These channels do several things simultaneously. They allow air to penetrate deep into the soil, providing the oxygen that plant roots and soil microbes need. They allow water from rain to infiltrate rapidly rather than running off the surface. They allow plant roots to extend deeper than they could through unworked soil, reaching moisture and nutrients at levels otherwise inaccessible. Soils with healthy earthworm populations can drain up to 10 times faster than soils without them. This is not a trivial number. In practical terms, it means the difference between a field that absorbs a heavy rain and one that floods, between topsoil that stays in place and topsoil that runs off as erosion. The earthworm, without any intention or direction, is one of the most effective flood management and erosion control systems in existence. And after rain, earthworms do something visible. They come to the surface. The precise reason for this behavior has been debated for a long time. The older explanation that they surface to avoid drowning in waterlogged burrows is only partly satisfying, since earthworms breathe through their skin and can survive submerged in water for some time. The more current understanding is that wet conditions make the surface accessible in a way that dry conditions do not. Moving through soil is hard work for an earthworm. The resistance of dry, compacted soil limits how far and how fast a worm can travel. When rain saturates the surface, worms can move across the soil much more easily than through it, covering distances in a single night that would take days of underground travel. Rain is, for earthworms, an opportunity, a window of low resistance movement that allows them to migrate, to find new areas of food-rich soil, to locate mates. So the earthworms you see on a pavement or a path after rain are not lost or confused or drowning. They are traveling, taking advantage of the wet conditions, the way a sailor takes advantage of a favorable wind, going somewhere with purpose in the only easy hours the weather provides. There is in all of this a picture of extraordinary interdependence. Rain arrives. Bacteria wake from spores. Fungi extend their networks. Earthworms travel. Plant roots are fed. Water infiltrates rather than running off. Nutrients cycle from dead organic matter into living plant tissue. The whole system, the microscopic and the visible, the bacterial and the fungal, and the animal and the plant, activates together in response to the same trigger, the rain. That is all it takes. A particular amount of moisture arriving in the right form, and the soil beneath a field or a garden or a forest floor comes alive in ways that most of us never see and rarely think about the next time rain falls on a patch of bare earth. This is happening beneath it, in the dark, in the quiet, in the warm, moist, teeming community of the soil. Everything waking up, everything beginning again. At the bottom of the world, it is snowing. Not heavily, not in the way that snow falls in a city or on a mountain range, in dense curtains of large flakes driven by wind, accumulating inches in a night. At the South Pole, on the high plateau of Antarctica, precipitation arrives in the form of tiny, glittering ice crystals falling from a sky that is often otherwise clear. A phenomenon called diamond dust. Precipitation so fine and sparse, it is barely visible, except when the light catches it at a low angle and the air briefly sparkles. Antarctica receives the equivalent of about 150 millimeters of rain each year, roughly the same as the Sahara Desert. It is, by any technical definition, a desert, the driest, coldest, windiest desert on Earth. And yet, it is covered in ice nearly 3 kilometers deep in places. Because the snow that falls there falls in temperatures so far below freezing that it never melts, it simply accumulates year after year, century after century, millennium after millennium. Each year's snowfall compressing the year before it, gradually transforming from fresh snow to dense packed snow to the intermediate material called firn, and eventually to glacier ice. The whole column of accumulated precipitation growing slowly deeper and deeper and heavier and heavier, pressing down on the bedrock of the continent below. This is the slowest part of the water cycle. Rain that falls in a tropical storm and finds a river can reach the ocean in hours or days. Rain that falls on the Antarctic plateau may not return to the ocean for hundreds of thousands of years. The ice cores drilled from Antarctica by scientists over recent decades are, among other things, archives of ancient precipitation. Each layer of ice is a year's snowfall, a compressed, frozen record of the atmosphere at the time it fell by drilling down through these layers and analyzing the chemistry of the ice at each depth. Scientists can reconstruct the temperature, the atmospheric composition, and the patterns of precipitation for hundreds of thousands of years into the past. The deepest ice cores drilled from East Antarctica contain ice that fell as snow over 800,000 years ago. 800,000 years. The snow that became that ice fell before our own species existed. It fell on a world where woolly mammoths would not appear for another 500,000 years, where the landscape of Europe and North America was shaped by ice sheets that would advance and retreat many times before the first humans crossed into the Americas. That ancient snowfall is still there, compressed in the dark beneath the ice sheet, carrying in its chemistry a record of the air of a world entirely unlike the one we know. The Antarctic ice sheet holds approximately 26.5 million cubic kilometers of ice. This is difficult to visualize, so it helps to put it another way. If the Antarctic ice sheet melted completely, global sea levels would rise by approximately 60 meters. Every coastal city on Earth, every port, every delta, every low-lying island would be submerged. The ice sitting on the Antarctic continent right now represents the single largest store of fresh water on Earth. Nearly 70% of all the fresh water on the planet is frozen in Antarctica. Accumulated precipitation by precipitation, snowflake by snowflake, over millions of years. The Arctic is a different kind of place, where Antarctica is a continent, a landmass the size of Australia and Europe combined, buried under ice. The Arctic is an ocean. The North Pole sits not on land, but on a frozen sea, the Arctic Ocean, covered by a shifting, fracturing, constantly moving layer of sea ice that thickens in winter and thins in summer, never touching the ocean floor, floating on several kilometers of cold salt water. The precipitation of the Arctic is, if anything, even sparser than Antarctica's. Over much of the central Arctic Ocean, annual precipitation is less than 250 millimeters, less than the driest parts of continental North America. But unlike Antarctica, where the cold is so extreme that almost nothing evaporates and almost nothing is lost, the Arctic Ocean is in constant exchange with the atmosphere above it and the ocean around it. Sea ice forms and melts. Open water evaporates. Snow falls and is immediately blown from thin ice surfaces back into the water. The whole system is dynamic in a way that Antarctica, locked under its massive, ancient, cold-compressed ice sheet, is not. What both poles share is a relationship with precipitation that operates on timescales entirely outside ordinary human experience. At the Vostok Research Station in East Antarctica, one of the coldest places on Earth, where temperatures can reach -89 degrees Celsius. The firn that falls today will not become glacier ice for approximately 2,500 years. The snow that is currently sitting on the surface of the ice sheet near Vostok, waiting to be compressed into ice, fell roughly at the same time that the Roman Empire was rising. The compression is that slow. The patience of the polar ice sheet is geological. It operates not on the timescale of human lives or human history, but on the timescale of the planet itself, and the ice is an archive not only of temperature and atmospheric chemistry, but of sound, or rather of silence. The air bubbles trapped in glacier ice as snow compresses, tiny pockets of ancient atmosphere, sealed in ice hundreds of thousands of years ago, contain samples of the air of ancient worlds when scientists drill ice cores and carefully crush or melt sections of the ice. These bubbles release their preserved ancient air. The composition of that air, the concentrations of carbon dioxide, methane, and other gases, tells the story of ancient climates with a precision and completeness that no other archive can match. Each bubble is a tiny sealed jar of ancient atmosphere, ancient air, ancient sky. The precipitation that fell to create the ice was not simply water falling from clouds. It was the sky making a record of itself. Every snowflake carried with it, when it landed, a sample of the air it fell through. And that air is still there, preserved in the cold dark of the ice sheet, waiting to tell its story to whoever drills down far enough to find it. In the Arctic, a different kind of record accumulates. Sea ice, the frozen surface of the Arctic Ocean, grows and thins and fractures and moves with the seasons. First-year ice, formed in a single winter, is thin and salty. Seawater freezes slowly, and as it does, some of the salt is excluded from the growing ice crystals and concentrated in pockets of very cold brine that drains slowly downward. Multi-year ice that has survived one or more summers without melting, has lost more of its salt, is denser and thicker, and carries in its structure the record of the temperature variations it has survived. Sea ice is also ecologically a surface, a strange, shifting, temporary surface between ocean and sky, but a surface nonetheless, colonized by specialized algae that grow in the cold brine channels within the ice, feeding the copepods and krill that feed the fish, that feed the seals, that feed the polar bears. The food chain of the Arctic begins, ultimately in the ice, in the dark channels of frozen seawater, where tiny organisms photosynthesize in a dim, diffuse light filtered through meters of ice above them, without precipitation, without the snow that feeds the ice sheets, and the temperature conditions that freeze the sea. This entire ecosystem collapses. The polar regions are not remote and irrelevant extremes of the planet. They are the planet's thermal regulators, the places where the excess heat of the tropics is ultimately dissipated into space. The engines that drive the ocean circulation patterns that distribute warmth and cold and nutrients across the entire globe. The snow that falls at the South Pole tonight, a few diamond dust crystals settling on a surface that has been accumulating for millions of years, is part of the same water cycle that moves through tropical storms and morning fog, and the clouds over a garden in a Florida suburb, and the mist rising from a forest in the early light. It is the same water, the same molecules briefly visiting the coldest and most remote place on Earth, being kept there for a very long time before the cycle continues. There is something profoundly calming in the scale of this. The polar ice sheet accepts its precipitation without urgency, without rush. It has been accepting it for millions of years and will continue accepting it for millions more, patient as nothing else on Earth is patient, keeping what it receives in the cold and the dark and the silence, the slowest rain, the most patient archive, the longest sleep. Let that patience be the last thing in your mind tonight. Something receiving and keeping and being still for as long as it takes. We have traveled a long way tonight. We have followed a raindrop from its beginning, a tiny droplet forming around a grain of sea salt in the dark interior of a cloud, all the way through its fall to earth, and then further still into the rivers and aquifers and ocean beds and forest floors and living tissues that it passes through on its endless journey. We have listened to rain from inside thunderstorms and desert blooms and monsoon seasons and the foggy shores of northern seas. We have heard it on other worlds, on frozen moons and gas giants and scorching exoplanets where iron falls in place of water. We have smelled it in the soil and read it in paintings and heard it in music that was composed specifically so that someone, somewhere, could sit with the feeling that rain makes and let that feeling be named. And now we have arrived at the simplest part, the part where the facts give way to the feeling, and the feeling is all that remains. You are here, right now, in whatever position your body has found for itself in this particular moment of this particular night. There may be real rain outside, or there may not. It doesn't matter. The rain we are sitting with tonight is the rain that lives inside all of this, inside everything we have learned and considered and allowed to settle, a kind of internal weather, as real in its effects as anything falling from a cloud. Your body knows it is time to rest. This is not a decision you need to make. It is something your body is already doing, has been doing since long before this moment, quietly and without your direction. The temperature of your core is dropping slightly, as it does every night at this hour. The thermostat of the circadian rhythm turning itself down degree by degree. Melatonin has been building in your bloodstream since the light began to fail. Cortisol, the wakefulness hormone, the alertness signal, has been falling for hours. Your nervous system is doing what rain does to an anxious afternoon, settling it. The parasympathetic nervous system, the branch of the autonomic nervous system responsible for rest, for digestion, for recovery, for the particular bodily state we call calm, has been quietly taking over from the sympathetic system that kept you alert and ready and responsive through your day. The sympathetic system is necessary. It is the system that makes you quick, that sharpens your attention, that prepares your body to respond to whatever the waking world demands. But it was not meant to run continuously. It was meant to give way every night to something slower and deeper and more generous. The sound of rain, real or remembered or imagined, facilitates that handover, not because it has magical properties, but because it carries a signal that is very old and very clear. A signal that your nervous system has been receiving since before you were born, since before your ancestors could name what they were hearing, since the first mammals huddled in whatever shelter they could find and listened to water falling outside and aloud. Finally, the readiness in their bodies to dissolve. Nothing is coming. Not tonight. The rain has arrived, and with it, permission. Let us take that permission slowly and seriously now, not as a metaphor, as something that is actually happening in your body right now as you allow your attention to soften. The muscles that have been slightly contracted through the day, in the jaw, in the shoulders, in the muscles around the eyes, let them release now. Not forcibly, not with effort, simply by noticing them and then allowing them to find their natural resting state. The way a hand unclenches when it is no longer needed to hold something. The breath will slow on its own if you let it. You do not need to slow it. You only need to stop quickening it. The body knows the rhythm it wants at this hour, and if you step out of its way, it will find that rhythm by itself. The way water finds its level when the pressure is removed. The thoughts that are still moving, the threads of today and tomorrow, the small unresolved things, the plans and the worries and the vague background hum of the mind doing its constant, restless work. Let them be what rain is to a landscape. Let them fall and be absorbed and find their way into whatever ground is available without you needing to direct them or resolve them tonight. They will still be there in the morning. Everything that is real and important will still be there in the morning. No worse for having been left for a few hours. The rain does not require the landscape to prepare itself. It falls on whatever is there, and the landscape absorbs what it can, and the rest runs off. And in the morning, the ground is different, softer, more receptive, more alive. And whatever could not be absorbed last night will find its way into the rivers and the sea. Your mind is the landscape tonight. Let the thoughts fall and be absorbed. Let what needs to run off, run off. And let the ground of your body simply receive what it can without effort. We have learned across all these hours together that rain is not one thing. It is a family of things, heavy and light, warm and freezing, dramatic and barely there, tropical and polar, convective and frontal and orographic, and every other form that falling water takes when conditions arrange themselves in a particular way. Each kind of rain is the atmosphere doing what conditions require. Each kind is the right kind for its place and its moment. And what this moment requires is the softest kind, not a thunderstorm, not a tropical downpour, not the driving horizontal har of a Scottish coast in November. Tonight, the rain is the kind that barely whispers, the kind that settles on the surface of still water without disturbing it very much, the kind that the forecasters call light rain, that the farmers welcome as a gentle soaking, that the gardeners hear from their beds as a soft, steady presence, and feel grateful for without fully waking up to appreciate. It is falling somewhere on the other side of the glass, or somewhere inside the space between your thoughts. It is falling on all the things we have visited tonight, on the surfaces of quiet oceans where freshwater lenses are forming and dissolving, on a field of young wheat, on the rooftops of old cities, on mountain slopes where it will settle into snow and wait until spring to begin the next part of its journey, on rivers that have been carrying the memory of rain from mountain to sea for longer than there were people to watch them. On all of it tonight, a gentle rain. And you do not need to know where you are in this geography. You are simply inside it. Inside the rain-soaked world, in a dry and quiet place within it. The sounds of falling water arriving from somewhere just outside the boundary of here. Steady and soft and entirely familiar. Every system in your body that was built to respond to this sound is responding now. The cortisol is falling. The melatonin is rising. The muscles are releasing their residual readiness. The heart rate is dropping to its long, slow night rhythm. The brain, that extraordinary, tireless organ that has been processing and evaluating and planning and remembering since the moment you opened your eyes this morning, is beginning to let its faster waves give way to slower ones, alpha waves, then theta waves, the long, slow electrical rhythms of drowsiness, of the boundary between waking and sleep, where thoughts become soft-edged and images arrive without being summoned, and the ordinary logic of the waking mind relaxes its grip. You are at that boundary now, or approaching it. The rain is with you. It has always been with you. You have been hearing this particular sound in this particular way, registering this particular safety signal for every year of your life and for every year of your ancestors' lives, stretching back to the first creatures that sheltered in the dark and listened to the sky emptying itself and felt the particular physical full body release of knowing that here, in this place, in this moment, there is nothing that needs doing, nothing that needs watching, nothing that needs to be faced until the rain stops and the morning comes. The rain is not stopping tonight. Tonight it goes on, softly and steadily, past the edge of sleep, past the place where you can follow it, into the long quiet. Let it carry you. The rain knows the way.